My name is Taylor Locker, and I'm the Deputy Director and Chief Scientist here at the Highly Automated System Safety Center of Excellence. We refer to ourselves as the HASS team. And we are very excited because our mission mandate from Congress is to help and work with the OAs on reviewing, assessing, and validating highly automated systems for safety. And when we think of AI assurance is such a critical and component piece. And that's what we're here to talk about and learn from a lot of the experts from the academic community on AI assurance, where we are, what do we learn about it, and where can we go together collectively. So as you can see on the screen here, we have the afternoon split up in 2 afternoon days, 11:30 to 4:30. We did that intentionally because we wanted to make sure that it was a good time so that our West Coast colleagues could join us at not 5 in the morning calls, since we're based out of the DC area. So we wanted to make sure we had that opportunity for everyone to have a nice chunk of the day to be able to spend time learning from these discussions. So we're going to kick off today with Robert Hampshire, our Deputy Assistant Secretary and Chief Science Officer of DOT, to talk a little bit about kick us off on getting excited in the keynote speech. Then we move into an AI assurance framework discussion by Dr. Wafang Yu, and he is our lead at Haas on AI assurance. So we're very excited for him to kind of lay out the framework that's going to be the basis of our entire time together here in this workshop series over these next 2 days. We kind of set up this the discussion over the 2 days, starting off with a panel discussion, which the first one will be focused on government AI safety programs, followed by 2 technical sessions on AI risk assessment and mitigation, followed by AI data assurance. And those are 2 critical components that Dr. Yu will explain in his framework discussion. Tomorrow, we'll be starting at the same time, and we're going to have a keynote speech by Brian Cronin, the director of the ITS Joint Program Office. Very excited to have him here, be able to talk to us about that space and AI assurance and what it means to JPO. And the panel that we're going to be kicking off tomorrow is going to be focusing on AI assurance research needs and priorities. So that's going to be a very fun discussion on kind of piggybacking up what we learned today and into that discussion with those experts, followed by 2 additional technical sessions, design time assurance and operational time assurance. So again, these are some major components to the AI assurance framework that we want to be able to educate, learn, and understand where we can go from here. We're going to wrap up tomorrow with the reflections and wrap up of what did we hear, what are some of the thoughts and questions. But one of the things I do want to pivot over to that's very exciting, we designed a bunch of questions to ask throughout these 2 days to help us kind of gauge where we are at in some of these activities, so that we can understand where we could make some of these research priorities and where could there be gaps in the AI assurance space that we can start to work together as a community to understand how we can move this industry forward with quality AI assurance and safety. So with that, I'm going to pass it over to Haley, and we're going to go ahead and ask the first question for everybody. And we're going to be using Mentimeter this week. And throughout the sessions and throughout all of the panel reviews, the sessions and everything, we'll be sparkling in these questions using Mentimeter. After everyone answers the question, we will then post the responses once we close the poll. Okay, so if everyone wants to open up Mentimeter on their browser, it's www.menti.com and enter the code 81205112. And with this code, it will open up into the series of questions. There'll be a first question followed by a second question for every question we answer. Once you answer the first question, which is basically what type of industry are you from, whether you're government, are you industry, are you academia, you identify that, and then you'll answer the first question. So here we go, Haley, I'll pass it over to you, and you can walk us through how this works.
Okay, great. Thanks, Taylor. So as you said, there's 2 ways you can get there, and we'll have the QR code and the actual code at the top every time. So if you lose it, don't worry. It'll also be in the chat if you need it. So first question is, what is your organizational affiliation? And there are a couple options. There's also another option if the ones listed don't speak to you. Feel free to enter an other option as well. So I'll give folks just a moment. I can see the numbers ticking up for this one. And that one will stay open. So I'll move to the first question to kick us off. So go ahead and turn on responses. What is your level of understanding of the foundational concepts and challenges in AI assurance? So I also want to say that your responses are anonymous throughout this workshop. So we do appreciate your candid, honest feedback to these questions. We also encourage you to use the same device throughout the workshop, whether that be your phone or your laptop. And you can just keep the browser open. That's also recommended so you don't have to skip through questions that you've already answered if you happen to jump back in. Okay, so give people 30 seconds or so to answer. And if you do happen to skip past it, you can jump back in with the code again. Not open for voting. Okay. Has anyone? I'm looking. Looks like people are responding. So maybe come back in if you accidentally. It may not have been open right when you plug the code in.
And since this is the first question, we can leave it open. We'll leave it here for about another minute or two, just to give everyone a chance to get used to the Mentimeter. And we'll make sure we get all the kinks out now. So as we go throughout the day, when we ask some more challenging questions, we'll be able to get your feedback.
All right. I'll give it just a little more time. Yeah, so please refresh if you didn't see it at first. We're only going to open the questions as we go along throughout the day, just so that they are asked at the appropriate time during the workshop. So looks like numbers are still ticking up. So I'll give another 20 seconds or so, and then we can show the results. And if you need the code, it's at the top of the slide shown here, or you can use your phone in the QR code. All right, I'll go ahead and I'll keep it open and show the responses so far. So it looks like we have a pretty good distribution here of folks with some familiarity with AI assurance and its related concepts. Some with very high, which is really exciting. I think folks will have some interesting things to share, and some with less familiarity. So that's a great mix here, I think, Taylor.
Yeah, this is great. And I think that's why we started with this question. We really wanted to kind of get a baseline of, where's all of our knowledge in this? And as we go throughout the week, we're going to be listing some very interesting conversations, whether the panel discussions that we're going to have, where we have teed up some really great conversation there, as well as some of the technical presentations. I think that's where we're going to dive into the weeds and start to understand, when we look at some of these AI components and AI framework, what does this mean to me? How is this framework going to help, help in the activities that I'm working on, assess these systems and ensure their safety, so that we can deploy these tools and we can use them for their benefit.
All right, I'll stop sharing and hand it back.
All right, thank you, Haley. All right, so that was our test run. So now we have everyone's experience in Menti. We're gonna have a great day, super exciting. So with that, I'm gonna pass it right over to Stephen, who's gonna make an introduction for our keynote speaker for today. Stephen.
Fantastic. Thank you, Taylor, and thank you, everybody, for your engagement and working with the technology here. It's my pleasure today to introduce Dr. Robert Hampshire. Dr. Robert C. Hampshire serves as the Deputy Assistant Secretary for Research and Technology and as the Chief Science Officer for the USDOT. Dr. Hampshire was previously an Associate Professor at the Gerald R. Ford School of Public Policy at the University of Michigan. He's also a Research Associate Professor in both U of M Transportation Research Institute, UMTRI, and Michigan Institute for Data Science, MIDAS, and an affiliated faculty member in the Department of Industrial and Operations Engineering. Dr. Hampshire's unique blend of engineering systems research with his public policy expertise has made him a leader not only in transportation research, but also on the disparate impact of policy decisions in transportation systems. This has led to important strides in our understanding of transportation equity. His research applies operations research, data science, and systems approaches to analyze novel transportation systems engineering, such as smart parking, connected vehicles, autonomous vehicles, ride-hailing, bike sharing, car sharing, as well as pedestrian and bicyclist safety. His research focuses on environmental impact, equity, and access to opportunities, and his work has been widely cited and covered in major press outlets. And Dr. Hampshire is a faculty member at Carnegie Mellon University beforehand, and he was also a visiting professor at the Massachusetts Institute of Technology, and has received a PhD in operations research and financial engineering from Princeton University. So Dr. Hampshire, with that long list of accolades, thank you so much for joining us here this morning, and love to hear what you have to say.
Well, Stephen, Dr. Zoff, and Haas, and everyone attending today, I really just a hearty welcome from the U.S. Department of Transportation. It's really great to see this continued series on AI assurance. That continues from November. I remember the first workshop I had the opportunity to drop in on to think about AI and AI assurance frameworks. and boy, has it grown as people are being admitted here in real time. Thank you all for being here. I think this next, I think 2.5 days are going to be engaging, certainly educational, but also it would be two-way street. All right, we really are in the phase of learning. We can learn together, and it's tremendous to be here with this community. Um, as Stephen mentioned, I lead the office of the Assistant Secretary for Research and Technology, as well as being the department's Chief Science Officer. I take that as a true privilege, and the colleagues that I here at USDOT, not just in OSTR, but across all the modes. It's just a tremendous honor and pleasure to work with the colleagues that we have at the department. Particularly as we're pushing to address some of the emerging opportunities, emerging challenges, particularly around the technology side and transportation. It's a true honor. We've built a team throughout the Office of Research and Technology and across all of DOT to really take on the emerging technology issues of our time. And those of you, we're always also hiring. So I always say, folks who on this call that represent some of the great minds and people with the great hearts as well. Please do look out for opportunities to join USDOT when appropriate. The office that I lead, OSTR, we really do work at this intersection of new and emerging technologies, but as well on data, policy, and statistics in a way that's multimodal. So our mantra is, a system of systems. We do believe that the interconnection, interrelatedness of all the transportation systems should be in the service of moving people and goods safely, efficiently, and equitably. As that's happening throughout our transportation system, we know that new emerging technologies like AI will be critical to that mission. But the ways in which we do that in the Office of Research and Technology, like I mentioned, helping to advance innovation and technology breakthroughs, also facilitating research and collaboration across all the modes of transportation. Our office sits in the Office of the Secretary centrally, but we work with all the modal colleagues from rail to transit to aviation to pipelines throughout the department to move the mission forward using research and technology. Also, when we think about using information and statistics, Bureau of Transportation Statistics is part of our organization. And also we have responsibilities on convening around workforce, education, and building the transportation workforce of the future. Many of you might be on the line now, but we host we fund our university transportation centers. We fund roughly about 150 universities in 35 consortiums, about $100 million a year. So that's 35 UTCs, University Transportation Centers, that are really the folks that represent, again, those on the cutting edge of innovation, technology, and evidence building. And so we rely and we really want to support our partners, that's UTC partners, but many of you other also who are on the line. We see this as an ecosystem that we're helping to lead, we're convening, and that's why today's meeting is so important. The AI Assurance Workshop that Haas and others here have put together is certainly a partnership. This AI consortium, it certainly is an joint effort between our ITS Joint Program Office, as well as FAA, OSTE organization, who are also co-organizers of today's event. And so what you'll see is, again, the Haas COE team, particularly, we've put together a collection of folks with the right talents, expertise in automated systems, particularly on the safety of automated systems. The mission of Haas is, again, to help work with the department, be our experts on how to assess, validate, the safety of automated systems. And certainly, as Taylor mentioned at the opening, AI is a key piece often of the AI automated systems. And how do we test, validate, and make sure we have assurance? And so you're going to hear a lot about that here today. But when we're thinking about AI, in the department, the president last fall released, as you know, the president's executive order on the safe, secure, and trustworthy use of AI. Embracing the opportunity that it represents, the global opportunity for our domestic industry that it represents, but also some of the challenges and risks that it represents. And so that executive order really put the charge to many federal agencies to get moving, move forward on AI, and we've done that here at the Department of Transportation. And certainly this effort today is one that it moves in the direction of helping educate and convene our stakeholders around AI. A few more things before I pass the mic back over to the Haas team. Part of the Department of Transportation, we've also in the research office, there's other activities in AI certainly that we're certainly engaging in and pushing forward that I want to make you aware of. One is we have an open request for information right now on the opportunities and challenges of AI in transportation. Perhaps someone can put that in the chat. That's an open RFI now. This request comes from DOT's ARPA-I. That's the Advanced Research Projects Agency for Infrastructure. A newly created ARPA-I from the infrastructure bill that's launched. And so they ARPA-I sponsored this request for information. So please, we would love to hear from you all from that. Thank you, Tony, for the RFI. That's open now until I believe July 12th. So please do take advantage of that. Secondly, we just had a small business research initiative, a SBIR program called Complete Streets AI initiative. This is a $15 million set of awards to develop an interactive decision support tools for state and local agencies as they're building out their complete streets and road network designs, particularly at the community level. Could you do that in a more automated, could you do that in a more integrated way? And that's the question that our Complete Streets AI Challenge represents. That opportunity did just close last week. I gotta say it was oversubscribed. The number of applications and small businesses that applied exceeded our wildest dreams and expectations, and so reviews are underway for that Complete Streets AI Challenge. Thirdly, I want to make you aware as well that we're planning in the fall TBD for an AI symposium hosted by U.S. Department of Transportation to really bring together what we've learned in the RFI, the insights from this community, but also what are some of the opportunities and challenges as it relates to AI in the transportation sector. And so I imagine many of you all on this call will also would be quite interested in that symposium. So please stay tuned for the dates and times for that. In closing, I really want to just encourage and thank you all for your engagement with the U.S. Department of Transportation around AI and transportation. This workshop represents a convening of some of the latest frameworks and concepts and an opportunity for us as USDOT and Office of Research to provide a place, provide a convening here, a meeting place for many of you all here to have this conversation, which is so critical for not just now, but for the future of the transportation system. So with that, I want to just thank you all for your attention. I want to thank you all in advance for your engagement and your partnership on this topic. It's one, again, it's moving so quickly, right? I think we're all certainly I saw from the Mentometer at different levels of knowledge and sophistication on this topic. So please do. We have a range of different folks and backgrounds, but I think this setting is ripe for learning. This setting is just so ripe for engagement and partnerships. And so that's why I'm so proud to have, that you guys are able to listen here a little bit from the opening, and just so proud of the Haas team, when it comes to, the mission of Haas to really be a leader in the validation, assessing, all testing of automated systems. And so with that, I'll turn it back over to Stephen, and just look forward to just a tremendous event in the next couple of days. So Stephen, back to you.
Thank you so much, Dr. Hampshire, for getting us started with those inspiring words this morning. I really appreciate it. So to get us into the meat of our program today, I'd like to turn it over to Dr. Huafeng Yu, who's a senior scientist with the Highly Automated Systems Safety Center of Excellence. And Dr. Yu, take us away.
Thank you, Stephen. And thank you, Dr. Robert Hampshire. We really appreciate your sharing your perspective for the AI assurance and all the progress of AI in Department of Transportation. So I will talk about our effort of AI assurance in our team and also our collaborations. So let me share my screen. Can you see my screen?
Yes.
Okay, great. So my name is Huafeng Yu, a senior scientist with Haas COE. I lead the AI assurance program and also organize a series of AI assurance workshops. So in this short presentation, I will give you an overview of our effort and also present our plans for the next workshops. So first, I want to talk about the challenges. This is always our very good motivation to develop AI assurance, not just in US DOT and also with collaborations with industry and academia. So currently, we see a lot of emerging challenges in safety of highly automated systems, particularly with the fast development and deployment of new technologies like AI assurance. And you can see that the technical challenges include very limited maturity, usability, and the scalability of assurance technologies, tools, and processes. And also, I'm sorry, just get back. Also, lack appropriate and sufficient requirements, evaluation metrics, criteria for the assessment of regarding safety goals and requirements, and then insufficient standardized requirements, benchmark testing platform, and simulation environments. We also have very slow adoption in comparison to the evolution of AI and its data when we consider the AI assurance technologies. And these are the technical challenges, and we also consider a lot of challenges in the government. For example, the lack of expertise, experience, tools, and talents for the assessment of AI systems, and limited access to the AI technologies, the data owned by other stakeholders. We also have the absence of powerful testing, evaluation environment, and the benchmarks. Of course, for the government employees, we also don't have or missing guidance and regulatory frameworks for all the AI research and the development. So we talk about a lot AI assurance. What is the AI assurance? So from here, you can see our definition for AI assurance in transportation. And of course, on the right-hand side, you can see a cover page of our recent white paper on an overview of AI assurance for transportation. So of course, the definition is a little technical, but in general, AI assurance means generating sufficient evidence to obtain a high level of confidence that AI systems will perform as expected without engaging in unsafe or unexpected situations. So we have a lot of examples based on the existing technologies or the current research. It includes verification, validation, safety analysis of AI components and AI-enabled systems. We also find a lot of AI assurance use cases, including performance and safety assessment of autonomous systems and their ecosystems. And of course, in these systems, we can see the perception, localization, planning, control functions. And we also consider the AI-based data analysis, particularly those data related to crashes or incidents of in the operations of autonomous systems. And so AI assurance is in the middle of the development by industry and the certification or self-certification requested by regulators. So it is a very necessary step to gain the confidence of these systems and also assure the safety of their operations. So let's talk about the general AI assurance activities. Here, you can see several key activities to consider in AI assurance. In this presentation, we will take we will take machine learning as our starting point. The first set of assurance activities are related to data. So data is playing a very important role in the whole process and the life cycle of the system. So first, data quality is one of the keys to perform AI assurance. And here you see two activities. The first one, data analysis, helps to understand the characteristics of data. And the data assurance is used to shape the data so that it has good quality or other characteristics to train the AI machine learning models and achieve expected performance or safety goals. The second side is related to the model itself. So here you can see we have two activities. The first model performance evaluation is related to the general machine learning properties like accuracy. And the second one, the model assurance, address verification of models, which consider the internal structure of the model, activation functions, and some other configurations of the machine learning model. So it's really focused on the machine learning model itself. And the third set of activities is related to the risks caused by the integration of AI into the system. We have two activities here, risk-based evaluation and risk mitigation. Risk-based evaluation usually uses technologies like AI risk identification and assessment according to expected safety requirements. And the next step is risk mitigation. So we use techniques like runtime monitors, fault detection, and recovery, among some others. AI risk techniques usually go beyond the machine learning component itself. We will need to consider the system level properties and accident or incident, potential incident or accident. So this is not a complete list, but it shows that the first set of activities, assurance activities we want to explore with our effort. From now, I want to give you an overview of our AI assurance program. So this AIA program was created by the HARS COE to enable the collaboration and coordination with all stakeholders. And also, we want to provide support to all of our operating administrations, the technical support or some other support. And there are a lot of activities in this effort, including the workshops, the definition of the concept, the AI assurance concept, establishment of collaboration and coordination in USDOT and also with our external partners, and also publish technical reports. Here, we already have this academic workshop for AI assurance. And with this AI assurance workshop, really want to empower participants with the necessary knowledge and tools to ensure safety, secure, and high-performance deployment of AI systems through comprehensive quality assurance, transparency, and ongoing risk management practices across all modes of transportation in the US. So let's have a small deep dive into the technical side of AI assurance. This is also one of our purpose to introduce the AI assurance framework. So you can see that here, we on the right-hand side, you can see the figure that we have 6 main concepts for AI assurance. We always start to explore with AI use cases. So this is the key to identify good enough assurance technologies. Currently, we don't have unique assurance technology to cover all the different use cases. So we usually need to consider the specific use case and then identify and develop specific assurance technologies. The second one is, according to the use cases, we need to do the risk assessment and mitigation. So we need to identify the potential risks that caused by the integration of AI systems, AI components in the system, and explore how to mitigate these risks by using the either existing technologies or development of new technologies. The next one is AI data assurance. As I mentioned, data is really one of the key to assure the expected behavior of machine learning and the expected safety level for the operations of our systems. So our data assurance here we explore how to guarantee the data quality so that we can train a good enough model for expected safety goals. And then the next two are related to the machine learning models. One is design assurance and one is implementation assurance. So design assurance is related to the design model, the machine learning model. So here we consider the design model at the design phase. So it's really about the verification of the trained machine learning model. And then the implementation assurance is related to several activities after the trained model, including the compiling, optimization, and also deployment of the trained model onto the target platform. So we need to consider the all the properties are always consistent during this implementation and the deployment phase. And the last one is to support for assessment of AI or regular effort. This is what we want to do to support our operating administrations and other stakeholders. So here, I want to discuss a little AI safety approach. So here on the right-hand side, you can see a diagram that we summarize from the most recent AI executive order. And so of course, we always need to consider the system and evaluation, and we also consider the different properties like robustness, reliability, repeatability, and of course, to verify these properties or check these properties, we need the testing and evaluation technologies. Some of them are at the development phase, and some of them also address deployment. And of course, on the right-hand side, you can see several safety objectives, including the function as intended, resilient against misuse or dangerous modifications, ethically developed and operated in a secure manner, and compliant with applicable federal laws and policies. So these are the safety objectives summarized for the general use of AI in our society. And in transportation, we do have specific safety objectives to meet. So that's something we want to discuss and also explore together in the future. Now let's take a look at the AI assurance framework. Here we consider the AI assurance from a life cycle perspective for the AI components and the AI-enabled systems. So here we have several basic life cycle considerations, including data requirement and safety assessment. So it covers all the phases from the design time to operation time, and also maintenance and some other activities. The next one is the design time assurance. So here we consider all the different techniques that we like a verification validation of the model, and also collection of data, data quality control kind of techniques in the design time. So it's really something we need to do before we deliver the product to our customers for operations. And then operation time is really about when the AI systems are deployed already on our street or in our national airspace. The techniques that we can use to manage unexpected situations, considering the uncertainties of the environment and the uncertainties in the system operations. And the last one, contingency management, is really about the last action we want to take when some fault or failure occurs. So I have some examples, like if we have engine failure, we will need to take a contingency landing action. Or for the self-driving cars, if we have unexpected problem for the planning and control, we will make emergency stop. So here, I want to talk about workshops. So of course, these workshops, with these workshops, we want to establish the cooperation and cooperation and between among all of our stakeholders. The coordination at this moment, we are performing the coordination of the different AI assurance efforts in DOT. Is not just for aviation, and also we consider surface transportation and potentially some other applications. And for collaboration, we want to collaborate with our external stakeholders like industry and academia. So you can imagine we don't have that big resource, talents to develop or assess AI systems. And we don't have that environment, testing environments, simulation technologies for the assessment. So we want to leverage all the expertise and experience from our academic and industry partners. So this will give us more capability. And with this workshop, we want to first understand the academic and industry's challenges, needs, and priorities. And of course, if possible, we will figure out how to work together in the future. And we also want to support the standardization regarding the safety of autonomous systems, like the unmanned aircraft systems or self-driving cars, autonomous trucks, buses, or railway trains. And there are several considerations. The first one is the national standardization effort by the government, including the NIST effort. There may be some other international effort also. And the second one is the industry standard. So we expect the industry consensus so that we can establish the standard process, technologies, and other aspects from the industry to work together to move forward. Here, I want to talk about our collaborators for these workshops, organizers. So we have 3 teams here. You can see them from time to time in this workshop. They help to organize the program and provide all the support needed for the questions, surveys, analysis, and the report. Of course, you already heard our HAS team, and we also have the Intelligent Transportation Systems Joint Program Office, ITS-GPO. So Bob Sheehan is our coordinator for ITS-GPO. And we also have FAA's Senior Technical Expert Program. So Dr. Zhongfa is our FAA representative to help this series of workshops. Dr. Robert Hampshire already mentioned our first kickoff workshop in November. So that is really the first effort in DOT to work together to meet and in the DOT headquarters and discuss what is the current progress of AI assurance in DOT. And we also invited our FAA colleagues to share their experience and lessons learned for their AI assurance effort. So including how the aviation regulations, the current status about the regulations related to the AI and their roadmap to build the to access the AI applications for the future certification of AI-enabled aircraft. So that's really a good start, and we have representatives from all of our operating administrations, and we exchange the perspectives. So that's really the first step. And the second step is this workshop. You can see from the agenda presented by Dr. Taylor Loughran. Most of our speakers are from academia, so they will show their challenges, their technologies, needs, and priorities in research from the academic perspective. And these technologies may be the potential solutions for our challenges of safe operations of AI-enabled systems. So we also invited several government AI safety programs managers to share their perspective on AI safety research in government. And also we will have several faculties to help us to have some conversations on the priorities and the needs from the research perspective. So in this workshop, we want to learn from academia and we want to learn the potential solutions. And for the next one, the industry workshop, it will be in fall. So we will invite industry speakers to share their challenges in the development of the real AI-enabled systems for the cars, trucks, buses, and aircraft. So when we consider in the industry here, it's not just the OEMs. We also consider the suppliers, true vendors, and also some other stakeholders like the state, local government. So we will work together and we will discuss together the how to share the industry challenges and find out how to address these challenges. So in this venture, we will have the annual workshop. It will be a workshop to review our one-year effort regarding the academic input and also industry practices. The idea is to be open to all public, all the stakeholders, not only academic and industry. So all the others are welcome to attend the workshop and share their perspective on AI assurance in transportation. So based on this workshop, we want to build a plan for collaboration among all the stakeholders. So this is one of our major expectations to have this series of workshops. And of course, from the academic workshop, we will prepare the report to summarize the workshop, and it will be published in public 1 or 2 months after the workshop. So in this workshop, Taylor already mentioned the several technical sessions. So here, I will just show you how they position in what I already explained, the AI assurance framework. So we have our 6 main considerations for AI assurance, and we also have the life cycle considerations. Now we just pick up 4 areas, 4 topics. The first is AI risk assessment and mitigation. Second one, AI data assurance. And then we move to data design time assurance and operation time assurance. You can see this is just the 4th list that we want to explore with academia. It doesn't mean that in the future, we don't want to extend to all the other areas and even some new challenges like large language models and generative AI. So these are the most explored and I would say researched from both academia and industry. So we have already a lot of tools and methodologies related to design time assurance and operation time assurance, but much less for AI risk assessment and mitigation, as well as AI data assurance. So for this AI risk and AI data assurance, we really want to work with academia and industry to explore new methodologies, to develop new tools. So that are the 2 areas we will want to emphasize in this workshop. Okay, so this is a very this is a very small summary of these topics. I already explained. Just to remind, for AI risk assessment and mitigation, we want to explore the AI risks caused by the integration of AI, including the source of the risks, the dependency between the risks and the other system components, also probabilities, severity, and also want to explore the impact of AI risk on system safety. So currently, we do have a lot of existing technologies for the safety assessment of conventional aviation or automotive systems. But when we consider to integrate AI, a lot of things changed. So we want to understand what should be changed or adapted according to the new AI challenge. And then for AI data assurance, this is quite a new area. Even from a lot of data scientists' perspective, it is not new. But we really, in this area, we really want to explore how data could be collected, generated to make sure that we can use them to train good enough or safe AI machine learning components. So it is a little different from the general characteristics of data, but we really want to figure out how the data have impact on the machine learning behavior. And according to the expected or intended machine learning behavior, we need to shape the data set from generation to collection. And of course, we also need to explore verification validation method regarding data and also build the data benchmarks. I believe most of the data assurance technologies are very closely related to the data analytics. So we will borrow a lot of ideas from that area. The next one, design time assurance, is really about verification and validation. So we will have several presentations tomorrow, and you will see how the machine learning components, particularly neural networks, are verified and validated. There's still a lot of challenges, but we want to share this research and get your feedback. We can figure out how to develop in the future. And we also want to consider safety requirements, verification properties, the different analysis simulation technologies. Particularly recently, we have a lot of new analysis and very realistic simulation that can help a lot. And the last one is operation time assurance. You may already heard runtime monitors, dynamic assurance in the past. Assured autonomy programs from DARPA, NSF, or NASA. So we will continue to explore these areas and consider the real operations of our aircraft in the national airspace and the self-driving cars on the street, and also the autonomous trucks, buses. We also consider other techniques like fault detection and architecture-based mitigation. So most of the technologies are really from the existing technologies, and we want to make necessary adaptations for the new AI challenge. Okay, so Taylor already showed the agenda. So I just want to say that we start with these 4 areas, but in the future, we will extend these areas to cover more topics. And also we want to consider the industry and the academic needs, challenges, and we work together to develop these new technical areas. So that's an overview of our effort of AI assurance and the workshops. So if you have any problem, just let us know. So you can find my email here. And with these workshops, we really want to establish the collaboration between the government agencies, industry, and academia. So we are very open to have any conversations with you. Okay, thank you. So I couldn't see the chat window. I will just stop sharing and
Thanks, Huafeng. I think that was a great way to get us started this morning, and really appreciate everybody's attention. So we have on the agenda right now, we have a quick break for about 15 minutes. So we'll see you back promptly at 12:45 Eastern, 9:45 Pacific. See you all in about 15 minutes. Thank you, Huafeng.
Thank you.
Alrighty. Well, I think we're ready to kick off the first panel on government AI and safety programs. So welcome back, everybody. Great session earlier with Dr. Yu and his approach to AI assurance framework. It's very fascinating, and I think that's what's really spearing ahead everything that we're going to be here to talk about today. So we have a very exciting panel. I'm going to start off with Dr. Trung Pham, from Chief Scientist with AI and ML at the US DOT FAA. We have Dr. Olivero Velasquez, Program Manager in the AI space at DARPA, leading some amazing activities. And then we have Guillaume Brat, who is the Robust Software Engineering Lead at NASA Ames. So I think we're going to have an amazing conversation today. And so to kick that off, I must ask each of you panelists the same question. And the question is, can you give the folks on the phone here an overview of the current AI safety programs implemented by your federal government agency? So Trung, we'll start with you.
Thank you, Taylor. Good morning. My name is Trung Pham. I work at the FAA in the area of AI and machine learning. We don't have a specific program implemented yet because we just started out, but we do have a document called AI Roadmap that I'm preparing, and that AI Roadmap is talking about the clear path to certification of AI in aviation and some long-term aspect of using AI in safety enhancement. and that document is about finished for internal approval, and the timeline is that we will release it for public comments as soon as possible, as soon as we clear with legal department. In addition to the AI roadmap, we also have the AI strategy document that was prepared by the Chief Data Office. And that document is guiding us on complying with the executive order on AI, specifically for the responsible use of AI across government agency.
Well, that is interesting. So, Guillaume, what's going on at NASA? Where do we see AI safety programs, helping support some of the activities you all are leading?
So at NASA, we, as you know, we have a small part that's focused on aviation, a big part that's focused on space. On space application, we don't see yet a whole lot of applications of AI or machine learning, I should say. AI has been used for the longest time to provide capabilities in terms of autonomy. Spacecraft need to be autonomous when they go to Mars or other far planets. In terms of safety, really, the work in AI safety is done within the aeronautics part of NASA. It resides in a project called System-Wide Safety that looks at safety in aviation, and AI and ML in particular are a big target. Again, the target is more autonomy than just AI. AI is part of the solution for it. So we look at it from that point of view. And I would say we, like the rest of the world, we awakening to the use of large language models and what we can do with them and what we should do and what are the safe aspect and secure aspect of using them.
That's great. Alvaro, what about the Department of Defense? What's DARPA up to these days?
So we're up to a lot of fun stuff. It really depends on which slice of the safety pie we're talking about, right? Safety has become a sort of umbrella term to mean all kinds of things, robustness to uncertainties, explainability of an AI system, trustworthiness, ethical behavior. It's an infinitely expanding bubble of different things. But we have programs in a lot of these different aspects of safety. So for example, I was managing the GUARD program, Guarding AI Robustness Against Deception. It's a program that ended about 3 months ago. And there we developed a lot of algorithms to measure how robust AI systems are to changes in their environment, right? Typically, we train these models on a specific training distribution of data. Naturally, when we deploy them, what they encounter is not exactly that distribution of data. So it's very important that they're robust to what they observe in the real world. So we developed some open source toolboxes that I welcome the community to take a look at. It's called ART, Adversarial Robustness Toolbox, and it has many different kinds of attacks and defenses to measure the robustness of these systems. On the human-machine interpretability side, we have the ACOLP program that looks at taking these LLMs. LLMs are sort of hard to explain. Can we extract a very compressed symbolic form that a human can easily analyze and then leverage to do human-machine cooperations with the LLM? And finally, we have a whole portfolio led by William Martin on scaling up formal verification of safety, right? When we talk about mathematically rigorously proving that something is safe, we rely on very, very expensive mathematical models that are restricted to tiny toy problems. So that whole portfolio looks at, can we scale these up, perhaps even to the size of LLMs, so that we can mathematically rigorously verify properties of LLMs. And I could go on and on, but I think that's a good sampler of safety programs.
That's great. I mean, so it sounds like there's just a lot going on, but also a lot of let's look at these different tools and see how we can apply and how they can maybe solve some of the needs we might have within our agencies. And so the next question I have for you, Chung, is what would be some of the biggest challenges you think government faces ensuring that these AI systems are safe?
There are many challenges. For me, I work on the technology side, so I would like to talk about technological challenges later on in the context of research. But for the general challenges that we saw that there is a lack of explanation of what an AI software can do or cannot do. And this is an important aspect that we must address for safety assurance to make sure that AI is safe in the path to certification. But one thing that compounded that challenge is the terminology that the AI community is using, and most of the time it's make AI sound like human intelligence. And I know and I respect that language is a convention of communication. So whenever we discuss in the technology sense, we define this is what we mean. But a lot of time we go to the public, we talk to the media, and we did not show the convention of what we mean. And the media is blowing it up, make it very interesting to the public to follow, and at the same time created fear from the public. And as you know, we work for government, so we respond to the public reaction. And this is something that will put more pressure on us for doing safety assurance for AI. And that is another challenge that we have, not directly, but indirectly. For the research challenges, I will highlight a little bit before I go deeper later on in the aspect of research. We want to assure that the learning component of AI is safe. It will deliver something that we train it to do, and it will not do something that we did not train it to do. And the public already seen many science fiction movies like iRobot, where the AI component eventually will learn and gain conscious by itself and learn to function with a different set of moral. So that is something that we need to, number one, technologically limit it, and number two, to assure the public that we are not in that direction, at least with the current technology.
Yeah, I agree. I think education to the public is extremely important. It's a fundamental piece of all technology, is how we communicate to the public that we serve, what this technology can bring and how it can better support, the things we do every day, and how we can trust these systems. And so I think taking that assurance approach is potentially a good way to kind of, walk through the process buildings. But Alvaro or Guillaume, what do you all see as some of the challenges? We talk about NASA and DoD. Similar challenges you all are facing? It seems like, or you guys have some unique challenges as well.
Guillaume, do you want to start?
Sure, because I'll be pretty much aligned with Trung. We're working with Trung actually a lot, and with Wafang Yu, we made the presentation. We did the presentation just before to try to solve some of these challenges. And actually, we have published a document that shows that explains what we see are the main challenges in VNV of AI. And Dr. Yu was actually the lead on this when he was still at Boeing before joining DOT. And then we published that last year. We mostly, since I belong to the part that focuses on aviation, we really take our challenges from industry and from people like Trung, George Romansky, or Wafang Yu, to see really what are the problems in terms of certification that a system that would use some AI would be safe. Okay. And I got to say, we're in the infancy. I mean, Alvaro was talking about scalability of some of those methods, and they're exciting, but really we're not there in terms of really being able to verify those systems to the level of comfort that we had previously in aviation systems, for example.
Right, and I can add to that. You know, we're definitely not there. I agree. You know, the formal verification community for decades, as I mentioned, has focused on small problems. At DARPA, we see it as our mission to focus on these seemingly impossible problems and likely fail, but you know, make progress along the way. I think some of the challenges to ensuring the safety, there are obviously long-standing technical challenges, but increasingly, I think we're also facing policy challenges resulting from the fact that, you know, industry is really eating our lunch when it comes to technological innovation. I mean, they move so quickly and they have access to a level of resources that within government we just don't have. I mean, if you look at the cost of training a state-of-the-art foundation model, the bill runs in the hundreds of millions on energy alone, not including labor and inference costs. That's just pre-training costs. So that sets up a dichotomy where you have big tech and the rest of the world when it comes to AI. I think we have some encouraging developments though. So you might be familiar with the AI pledge from the White House, brought in big tech companies. You know, they're voluntarily agreeing to collaborate with government to make their systems safer. And we're seeing some of that already through OSTP, right? The Office of Science and Technology Policy, where they're enforcing watermarks on some of these big tech companies so that we can at least detect when a piece of content has been generated by an AI versus a human, right? So I think that's a very good start. And I'm hoping to see those government industry collaborations flourish into safe AI.
I think that's a very important piece.
Which we are very far from, far from.
Yeah, that's why we have these sessions, is so we can talk about them, because we have to work together. And I think collaboration is a key component for us, you know, to have these dialogues and discuss. So with that, I'm going to quickly turn the mic over to Haley, and she's going to poll the audience for our first question for this panel session. Haley, mute.
Oh, thanks, Taylor.
Yep, there you go. Got it.
All righty, time for question number 2. Okay, so in the chat, you'll see how to access this again, or you can use the QR code with your phone or the code listed at the top of the slide. So same approach as it was before. It's the same code the whole day as well, so you can keep it open. So question number 2, now open. How effective are collaborations between AI researchers and experts from other disciplines in advancing AI assurance research? So I'm going to make sure folks have enough time to respond. So I started the timer. So again, please give your candid response to our questions. Your responses are anonymous. We'll just show the aggregated results after the period here.
Are we on the panel supposed to be answering these, or this is just for the audience?
It's just for the audience, but you can if you want. We're not going to hold that back.
I have my opinions on this question, but if it's intended for the audience, then I don't want to bias anybody.
Well, we can talk about that opinion at the end of the 20 seconds here, because that was actually going to be one of my next questions leading into this conversation.
Mm-hmm.
All right, I see the numbers ticking up here. We're almost at 100 responses, so thank you, folks. A couple more seconds, and then I'll show the results. All righty. Okay, so we have a bit of a mix here. Some say very effective or somewhat effective, but also a pretty heavy skew towards not too effective. So it's actually pretty split.
And this is kind of, you know, I guess we can kind of expect this type of response, because that's the whole purpose of really diving into this event, you know, this topic together. So, you know, Guillaume, you know, let's pull that thread a little bit. You know, what is government, you know, and collaborate with private sector organizations to promote, like, how does that work? How would government and private sector work together to promote AI safety?
So before going to this, let me really address this question.
Okay.
So a lot of the verification and validation for complex system was done with like using formal methods. And I set up a group at NASA working on this. And really, we had formal methods researchers most of the time. When was time to come and address the AI assurance part, we had to operate a shift in the staff we had. Progressively, we really injected more and more AI researchers into the group because they have the deep knowledge on how those systems are working. They can also bust the myth about those systems and really explain where the problems are. So that's one part that's answering the question. And my answer to your question was somewhat effective because we integrated those people in the group. It's still hard to get a really good dialogue between assurance folks and AI experts that are outside in the community. In terms of how we work with industry, for us, it's key. It's really key to see first what are the system that industry are thinking of fielding, because the field of AI is just so huge. I mean, it goes from the simple machine learning algorithm, supervised offline training, to those large language models nowadays. So you really have to restrict what you can address, what you're going after. And working with industry is essential for this. That's why we had that roadmap that we created where we ask industry where they were going. Basically, what are they planning on fielding from the next 5, 10, 20, 50 years? And then we're working with both. We're working mostly with the industry in aviation, and we're trying to work with the traditional aviation industry, the Boeings, GE type of companies, but also with the new entrants, because the new entrants have a mentality that's a lot closer to the big tech that Alvaro was mentioning. So it's a very different point of view. You had a traditional industry that was where safety was really ingrained, and they came from that place. Whatever system they were working on had to be safe. So they're very conservative in the use of AI. Then you get the new entrants that believe everything is data. We need to go after it, field it. We'll see what the problems are. Very different in terms of mentality. So we're trying to work with both.
That's a great point, Alvaro. So what are your thoughts?
Yeah, I mean, generally the cross-pollination of fields is of course desirable, but when it comes to AI, it can go in one of two very different directions. So before I went to DARPA, I was at AFRL, the Air Force Research Laboratory, and there it was very fashionable that whenever a new problem popped up, people would just say, "Oh, can we use ML for this?" Before they even asked, is there the right kind of data for this? Before they asked, do we actually need predictive models, or do we understand this problem well enough to solve it with classical methods? No, just ML is the hot thing. Can we throw ML at it? Which is actually counterproductive. So in that case, it would be ineffective to bring in the AI view. But in other domains, right, if you know what you're doing, it can be extraordinarily effective. So we've seen this, obviously, with in biology, we've seen this with protein folding. If you look at DeepMind's history of AlphaFold, AlphaFold 2, AlphaFold 3, it was a collaboration between biologists, chemists, and AI people. The AI people brought the AI models. The chemists said, this is a valid protein folding angle. This is what the van der Waals forces are that govern how different parts of the protein interact with one another, and so on and so on. We've seen it in material science with GNOME. So I think it's very important, generally speaking, to understand when AI is useful. And if you understand that, then the cross-pollination and the collaboration across different fields can be tremendously fruitful.
Yeah, I mean, that's a good point. And so, Trung, what's your experience been with FAA and the things that you all are leading in the AI space with the FAA and the industry community?
Yes, when we talk about collaboration, generally we mean working together, but working together with people mean different things. For example, working with people from different government agency, we normally tend to have communication. We want to share the result of our knowledge and our investment in research so that we don't have to repeat the funding unnecessarily. And when we talk about working with university, you have some funding for research grant that I will be talking later on. It's not unlimited, but at least we have something to motivate the researcher from university to work with us. And when we talk about working with the industry, we saw a different form of collaboration. Sometimes we came together in the same public forum to share experience. Sometimes we work together in projects, for example, certification project, where a specific company applying for certification will open up every aspect of AI development that they might not be willing to share in public forum. And that will allow us to figure out what is the best way to ensure or assure safety of the AI. And sometimes we have companies just casually develop a specific application, not a whole aircraft, and they can work with us through projects of product approval. And many of them already decided to come to us not just for the approval of product that they will be marketing, but to help us understand the nature of AI in aviation and to help us develop a clear path of assuring AI in specific project before we will be able to generalize that understanding to policy. So there are different type of collaboration, and depending on who we collaborate with, we will choose a specific collaboration model to maximize the intended effect.
So, I mean, as you guys are working with industry, a lot, and it's very effective ways to be able to work with them in these different pockets. How would you say we as government need to work on the standard side? Like, what is NASA doing on the standardization and working with industry? Because this is all new, and I think Alvar, you tagged on this earlier. But what is NASA like? What's your approach when it comes to standardization and working with industry in this very new space, emerging space?
So working on standards is always it's always tricky. Basically, they come up with standards using it's really government, industry, and research coming together to come up with the standards. So we follow we have people following every standard committee that's more or less related with AI. We have people embedded in the process. For example, in G34, we have people that are very active. In other committees that are more like integrating the result of AI at the system level, we are there too. On runtime monitoring, all the aspects that more or less related, we have somebody following and participating. Are we leading? No. G34, I think, is really right now pushed by the Europeans. Maybe the US should be more active in this, and our government should be more active in this. But in general, we a little bit one voice among many in those committees, and that's the problem. It's driven by personal interest, so it's hard to make a significant contribution. But when we do research in assurance, in safety assurance, we usually try to publish our findings publicly, or at least with government first. We have an example of this at the end of the month. We're going to publish a report that could help with the standards for AI, for ML, the use of ML in aviation. We are going to first send that to our government partners, first DOT and FAA. Alvaro, if you want it, you're welcome to contact me. We'd love to have your feedback. And then we'll
I would love
publish
to
it.
participate.
Yeah, great. So, and we'll publish it in September, the final version where we fold every comment that we have. We're not going to pretend that we address everything, that we're going to give standards out of the, full standards, but I think it'd be an important contribution to the discussion in that respect.
Yeah, Alvaro, what's your take on standardization and participation?
We don't really do much standardization at DARPA. I know NIST has been developing, there's the recently established AI Safety Institute. They've been developing some guidelines for AI safety. There's also the NIST AI RMF risk management framework. I think developing these standards are important. It's just very challenging because the technology moves so quickly that it means we would have to be updating these standards quite frequently. Mm-hmm. And it's also challenging for the technical people to distill those standards into a form that is technologically meaningful, right? Some of the standards will say something nebulous about safety, and then it's hard as an actual scientist to say, okay, what's the mathematical model of this thing they're trying to get across in the standards? But I think that's a normal, healthy tension that's always there between the standards and their technical manifestation.
That's a good point. That's a good point, Trung. So in the FAA aviation community, as you engage with them on AI systems or components, what level of standardization or interaction on, consensus developed standards do you guys participate in?
We have constant communication with all the aviation standard organization. As Guillaume earlier mentioned about SAE G34, they are currently working to develop a development assurance standard for AI, and we closely monitor, communicate, and participate with them as well as with the other standard organization. And we respect their autonomy. So like Guillaume said, we're not going to tell them what to do, but we do want to share with everybody the understanding of what it takes to provide safety assurance to those organizations as much as possible. As you know, we are in government sector, so everything we do is in public domain. So we like to share that with everybody to create the understanding of what it takes to provide safety assurance. And like Guillaume mentioned of G34, their next meeting will be in Paris in June, and I plan to be there to convey some of our understanding about AI development. And I'm currently working with Guillaume on preparing the message so that we can effectively communicate with them.
Are you going to stay for the Olympics?
No, I don't have the budget for that, and government will not pay.
Yeah, it's that's exciting. So again, one of the other questions I have, leading back to what we just talked about a little bit earlier, as we are participating the best way we can with industry on standardization by sharing results, sharing research, output, sharing data, helping the standards bodies kind of think about what standards are missing or what may need to be future developments. Alvaro, my question to you would be, how does government stay ahead of this technical advancements to ensure AI safety? What are things we can do if industry has a lot of resources? What's then our role?
Right. So there's a very interesting lesson, I think, that we have learned in terms of where we should be focusing on when compared to industry. So you might recall early last year, Meta's Llama 2 weights were leaked, right? Their parameter was leaked. I don't know if that was intentional or not, but it got leaked out to the community. And of course, the rest of big tech, these were all closed source models. Nobody really knew what the parameters were. And we saw this magical thing happen where within the span of, like a couple of months, the open source and the academic communities went crazy and started publishing extremely efficient methods to fine-tune that leaked model. And I would argue they published those very amazing methods in part because they were constrained by the resources that they had, right? They couldn't be intellectually lazy and just throw $10 million of compute at it. They don't have that compute. And so I think that's a lesson that's part of a broader picture of investing in resource-constrained AI. I sometimes think that the first person to discover a 10 million parameter, very effective foundation model will completely change market dynamics, will completely end the gatekeeping of the state-of-the-art models by big tech companies. And so that's where I think we should focus on.
Trung, what are your thoughts?
Well, I have many private conversations with companies from the aviation industry. And what I found is very interesting. I went to technical conferences like AI-GOP, and I saw that they had the wrong perception that it's us versus them. They develop, and we make sure that on our side, we make sure that it's safe, so it's against each other. But actually, it's more collaborative. For example, one project that we work with one company was to look at the way they process digital images for perception. And like Dr. Hoa Feng, you mentioned earlier about analyzing the training data, we discovered that we can analyze the training data, but it takes so much computational resources. Like if we are dealing with a set of 50 million high resolution images, it might take forever to run an analysis program. So the company we are talking to, they offer their cloud computing platform for us to use so that we can push computational efficiency further. For us, we really appreciate that level of collaboration and cooperation, but we do have our own cloud computing platform in our tech center in Atlantic City. And I want to make sure that before I take advantage of what the industry is offering, we have to get our act together correctly in a small scalability test before we go on a high capacity cloud computing platform. That example show that the industry has vested interest in us to make sure that we are successful in safety assurance of their product. So implicitly, we see each other as partner for public safety.
So yeah, I think that's like excellent. And I'm glad you brought up the tech center. What a cool place. I've been there recently and I got to meet a lot of the engineers there. It's amazing to see the work they do. But Guillaume, back to NASA, how does NASA stay ahead? I always think of NASA already being ahead, and then all the technology that comes out of what you all do spin off into all these innovations we have in our community today. So how does NASA stay ahead, and especially when it comes to AI safety?
The key for us is to have our own expertise in-house in that field. If we have AI experts, then we can keep up with the advances, and we know what's going to come and what's real, what's not real. I work in a division that has been created for AI, for artificial intelligence. It was created 30 years ago. So we're living in AI all the time. I mean, in the division. My group is focused on the safety and assurance of AI, but we have groups that are actually pushing the limits of those algorithms. And we are not limited in terms of computing resources like Trung was describing, because we also need high computer performance for even the science we do at NASA. So we have both of those ones, meaning that we can actually really explore and see what those AI algorithms can do. This said, I'll come back to the big tech. They have such an enormous amount of money that it's really hard to keep up with them. I mean, really hard. They can throw tons of people at the problem, tons of people. I'll share one experience. I lost, I think, 6 researchers to Amazon just because they're offering salaries that we cannot offer. And they didn't take the worst ones, I gotta say. They took good ones. And we're gonna keep losing some, and we're gonna keep losing brain power. But somehow we have to keep brain power. NASA got an advantage there, is that we make people dream. So we still have access to the young researchers that have big, bright eyes looking at NASA. I'm going to do cool stuff. That allows us to attract them. But it's over time, we're going to lose that competition with big tech. That's the biggest obstacle that we have right now.
Yeah, well, it's
and
very important.
NASA as a I would say another problem on top of this is that we are in the Silicon Valley where most of the big tech is, where the cost of living is enormous. So it's very hard to get young researchers to actually be able to live where they will work. Being able to work remotely is part of the solution, but that's another problem that we're facing to try to keep up with the advances of big tech.
So that's going to lead directly into our next question. So I'm going to bring Haley back here to walk us through our next question for all the folks on the phone. Haley.
All right, thanks, Taylor. All right, it's poll time. Let me pull it up. Question number 3. And I would encourage folks, if you can, please respond to the poll. Your input is extremely valuable to us. So an appropriate amount of resources are currently being directed to AI assurance research that is of the higher risk, higher reward nature. I will set the timer so folks have enough time. I'll open the responses to see the distribution after this period. All right, so thank you. Again, I encourage you to respond if you can. This is on kind of a Likert scale from strongly agree to strongly disagree. You can also say neither or don't know. Totally valid responses. And I will keep emphasizing that your responses are anonymous and are aggregated. So please be honest.
So it's great how we just tailored the previous conversation right to this question, because this is where we're going next. So
Great.
After we see the results, it'd be great to see the panel. If you guys have any reflection on what these results come out to see, if you agree or disagree with, the distribution we're about to see.
Awesome. All right. We're going to the end. So let me show responses. Okay. So it looks like we're skewed to the disagree side on this one a little more heavily. Interesting.
So does that map with what you all think? Makes sense?
It does. At least for me.
I think the assurance piece, again, similar to the safety piece, can mean many different things. Typically, when I think of assurance, I think more on the V&V side of things, more on the formal verification. And if that's the case, then I disagree. But if assurance here is meant more broadly to encapsulate safety, which again includes test and evaluation, robustness, and all these other things, in that context, I would agree. Because after all, we have, the DOT&E, right, Department of Test and Evaluation, that has been stood up. That was an enormous investment. The different branches of the military, their funding offices has some test and evaluation portfolio. And at DARPA, we have several assurance programs, including one of my own, which is called ANSWER, Assured Neurosymbolic Learning and Reasoning. So I think it's more a matter of trade-offs. If we wanted to fund more in AI assurance, where would we be comfortable taking away from? And I'm not sure what the answer to that is.
I think that's a great question that we could maybe ask ourselves after these next 2 days, because there's a lot of presentations that are going to happen after this one and all afternoon tomorrow. They might dive into that conversation, might say, is it more data assurance, more design time assurance, risk mitigation? I mean, there's a lot of components to AI assurance, like you said, especially when you focus on safety. I think there's a lot we can do there as a community, and I think that's why everyone's participating virtually with us, so we all can talk about it and figure out where we go. So, question for the group here, what specific research projects or initiative are currently underway that you may want to highlight that kind of fall into this space that, whether the resources are there and there's a lot of momentum, or hey, there's this new topic area that we're looking in and seeing if this could be a valuable new area to focus on with our community partners.
I could start. So I have a program that's kicking off in July, actually, brand new program. It's called TIAMAT, which is Transfer from Imprecise and Abstract Models to Autonomous Technologies. And that's a mouthful, but it's basically, how do we transfer autonomy from simulated environments to the real world when the gap between the two is very large? Because right now, the successes that we see, and I include autonomous driving in this space, rely on understanding your target environment very well, and being able to model it very close to reality so that you can sort of plug and play into the real platform. But real autonomy should be adaptable. We shouldn't have to understand every little detail about the target environment. And in fact, even if we look at autonomous driving, where does it work? It works in geofence locations like San Francisco, where companies like Waymo have collected tens of billions with a B miles of simulated data and tens of millions of real world data. So they have really good predictive models for pedestrians, for other vehicles. And so that gap between simulation and reality is made smaller and smaller and smaller. But you can't take a Waymo vehicle from San Francisco and put it in New Delhi. It won't work, right? This is not real autonomy. I think that we have a long way to go before we can reach real autonomy. And that is a big piece, I would argue, of safety. If we want autonomous systems to be safe, they have to be robust to the differences between what they encounter in one environment and another. So I'm very excited to see where the TIAMAT program goes. Part of the reason why I was reached out to do this panel was because of that TIAMAT program. And in fact, I think there could be very interesting transition pathways to the DOT. So I would be happy to discuss with Huafeng and anyone else that's interested in that direction.
Yeah, it sounds like a very promising area, especially the surface transportation is very dynamic. There's the ODD is just widespread. There's a lot of different environments. You got to think of like target environments, rail crossings, highways, arterials, with the different vehicle types that may traverse those roadway systems and all the different objects that are always changing, work zones or incidents on the road. So yeah, there's a lot of, I think the environment, the target environment is a very important, I think, area to focus on. So Trung, what are some areas that FAA is really, research projects that you might want to highlight or initiatives that you all are working on?
Yes. I guess we all know that everybody has limitation, especially with funding. But at the FAA, we have invested funding in research on AI long before we even had discussion with AI. If you recall, many years ago, my counterpart, George Romansky, chief scientist in software, he collaborated with Michael Holloway from NASA, talking about anticipating future technology that comes in where existing regulation cannot ensure safety. What do we do? What are we looking for? So it's still an ongoing project that Michael Holloway and George Romansky can elaborate more in terms of the overarching property. But then we began to notice of the trend of using machine learning to develop a system. So we invested some research money to work with the industry to develop some aviation system through machine learning. Number one, to benefit the specific area in aviation, but number two, to provide us more insights into such AI system that we can figure out how to do safety assurance. And recently, when I came in at the FAA, I established some theoretical research project with university to tie up some loose ends. For example, you heard Dr. Hua-Feng Yu talking about extracting characteristic of a system through the training data, but we don't have the assurance that the training program will deliver a unique result. So we might be able to extract characteristics from the training data, but how do we know that it's associating with the system that the training software is delivering? So that loose end, I gotta get it to university researcher, and hopefully they can help us establishing that missing link so that we can provide credible explainability of the system that is an important component for system verification. And looking into the future, we work with many industry to push for more research in the use of AI for and safety enhancement. Is an ongoing project, but many industry company already established initial research. They are not willing to talk to the public because of proprietary nature of their research, but they're willing to talk to us one-on-one, knowing that we are not going to review their trade secret. Mainly, they wanted to get us up to speed to prepare ourselves. So right now we are in private conversation with those companies to share what we're looking for, what they have been doing, and what we want to do to move forward. And we are collaborating with different government agencies. Each of us have our own funding, our own mission, and our own objective. So right now, we collaborate through communication and sharing so that we don't have to duplicate the effort. But with the executive order on AI coming from President Biden last year, collaboration will be more prominent. And I hope that we will have some collaborative project later on beyond communication and sharing.
No, I think that's great that you guys are having those dialogues and learning, like what does industry know about this technology? How are they applying it? I think that's important because it helps the government prepare our resources, especially when we talked about our workforce, GM earlier, how that's kind of suffering right now. But I want to go back to GM now with NASA. What exciting, new initiatives you guys have currently underway that you're working on in the AI assurance space?
I'm going to disappoint you in terms of new because we've been at it for a while. But we're going to keep investing into assurance of AI, especially for aviation, for the aviation side. And that's going to be done mostly under the system-wide safety project under a program that's called Airspace Operation and Safety. That's where it's going to live, and that's where most of the investment is done from the NASA point of view. We will try to expand that to address space applications, but we will focus mostly on aviation, which is an easier topic than I would say autonomous cars, where the context, the environment is so open that it's daunting.
Yes,
really.
yes.
Aviation is much more constrained, I gotta say. So in some sense, it's easier from our point of view. From the space point of view, if we were apply it to space, it would be even easier because the context is very limited in that respect. Once you realize at NASA that once you landed your spacecraft on the planet that you were aiming at, then you're happy. That's success. Yep. Doing science after that is a bonus. So AI will play a limited role in this, I would say. So collaboration is a big deal. I mean, Trump mentioned it. We're not going to solve the problem alone. We need to work together and try not to compete, but be complementary to each other. And that's a directive that we get from NASA headquarters, that we really need to figure out what the other government agencies are doing. And I think we have a great conversation with Strong, and we have a great conversation with Wafang. A bit less with DARPA. Alvaro, we probably should be talking a little more. We've worked with you used to have at DARPA, I think, a program called Autonomy Assurance, or Assurance of Autonomy.
Assured Autonomy, yes.
Assured Autonomy, yeah, that finished like 2 years ago or something like this. Then we had collaboration, but it kind of died off after that. But if we want to make headways in this, we need to work together. That's for sure.
Yeah, I think, and even Trung talked about global. You talked about global. Collaboration is important. So I'm going to bring Haley back in here for our last question to ask the panel, and to ask the audience here. So Haley, back over to you.
All right, poll time again. Same rules, same code, 8120-5112. The poll is now open for question number 4. Let's see if we can get a higher number than the last question. So how effective is the global collaboration among researchers to standardize AI assurance methodologies and best practices? So we're on a scale from very effective to not at all effective, and don't know is absolutely a valid response as well. All right. Oops. Let me fix my timer.
You'll be here for 43 more minutes, everybody.
Yeah, I don't know why they wanted to give folks a lot more time for that one.
That's okay.
Let's keep it. I'm not sure. Okay, I think I'll just watch the numbers here. Roughly 60 seconds to answer this question.
As GM said, we'll just land it on the planet. That's the goal. Get it on the planet. And then hopefully get the science back to Earth.
Yeah, it's a bonus.
It's a bonus.
Yeah, I'm going to turn that off and give folks a little bit more time. I think we had 107 on the last question. So if you could please be awesome if you could answer. Your input is extremely valuable. Responses are anonymous. And if you have any trouble getting onto this Mentimeter, please let us know in the chat. And I'll go ahead and start showing responses. All
right.
Keep it on though. Looks like the highest number falls at not too effective on global collaboration, but there is.
Does that make sense to you all? Your instant reaction here.
It does, and I would say for me, a big impediment to collaboration is the lack of case studies. We need to provide researchers access to use cases, data, so that they can really try to make headways. It's very hard for a researcher in university to get the data that they need, or the case studies that they need to do effective research.
I would agree with that. Yeah, I think the global collaboration from an academic perspective, I think is fine. It's very common to see international groups collaborate. From a government perspective, I know the EU has an AI Act, so it's good to see that they're at least taking a stab at it. But it's generally very tricky to collaborate across agencies, across borders. They have very different regulations when it comes to things like classification, what you can talk about in which setting. So that makes things a little difficult. So I would say it hasn't been that effective, but I'm hopeful that it's still too early and that we can change that.
So let's talk about not the borders outside, but let's talk about the borders within. What are some of the interagency working groups or committees that are focusing on AI that you all are participating in?
And it's an interesting question. We have what we call an RTT with the FAA that's focusing on assurance of AI. RTT stands for Research Transition Team, meaning that whatever NASA's research is being done, it should be transitioned to the FAA at one point. But I don't think it's the most effective way of collaborating. Really, we've been a lot more effective with one-on-one collaboration with Trung, for example, or with Wafang. And giving them access to our researchers directly is also a great way of collaborating. So the official channels, frankly, it's nice. Management can use them to claim success. But from a point of view of effectiveness, direct access to researchers is better.
I completely agree with that. I think, and especially with some of these agencies that become too large, if you go through the quote unquote proper channels, you don't really know where you're going to end up. It's typically best to leverage your own relationships in these agencies. One example is, under my GUARD program, the adversarial AI program, we're transitioning that tool to the CDAO, the Chief Data AI Office for the DoD. And then they sort of do the heavy lifting so that our tools can be used by anyone across the DoD. So I don't know to what extent you would call that a committee, but it's an interagency collaboration, leveraging our own relationships. Yeah.
I just want to go back to that point about global collaboration first. We do have global collaboration with different regulation agency. I have one-on-one conversation with our counterpart from EASA in Europe, with the UK Civil Aviation Authority in UK, with Transport Canada, with Brazil's ANAC, and with the Asia Pacific region, and with the Middle East region. We are in constant communication to share our perspective of regulating AI, what we know, what is necessary and what is not necessary. But also, when we talk about collaboration globally, we talk about international companies from the industry, but the boundaries seem to be blurring because, for example, when we talk about Airbus in Europe, immediately they said they had an office here in California. Or when we talk about Boeing in Seattle, they have their presence everywhere. So all the suppliers, they have their presence everywhere. We talk to them constantly to share knowledge. And thanks to the new technology that we started to use during the pandemic, we can have virtual meeting online that make it easier for us to see each other, communicate and share information that wasn't possible before that, when we were required to travel across the globe to meet with each of the company. So now, if you look at my schedule, every day is filled up with conversation with international partner, international companies. Mainly, we share the same objective of safety in aviation. So we will continue to do so, and we will continue to push the same model with different government agency. I started to work with Guillaume, and I'm looking forward to work with more, but we do have constant communication with the Department of Defense. I'm not sure if that person, Glenn Harold Carter from the Department of the Army, we work together with him. He had a online forum that we meet to discuss a safety issue with AI every month from the government perspective. So to emphasize, we work with everybody thanks to current technology that doesn't require us to travel to meet with people.
I mean, that's great. So, I mean, one of the other, and I think global is important. It's important for us all to talk to our global partners, to talk together, to talk to our own internal agencies. But here's the last question. I'm going to go a little off script because I think it's going to be a fun question for the folks that are here joining us today that have been really listening to this amazing conversation as we've driven through like everything. So what would be each of your advice to grad students or engineers in this space and how they can get involved in helping solve some of these AI assurance problems, where would you tell someone where they should start?
I'll start
Well,
with that.
Everyone wants to
If
answer.
you
All
don't
right,
mind, Trent.
go for
I'll
it.
start with that because I got an opportunity next week. So next week is the NASA Formal Methods Symposium organized at Ames. And I'm actually going to do your job and run a panel on AI, VNV for AI. I would say start there, where I've invited people from government, from academia, from industry, and I'm going to try to pin them down about topics of interest for researchers, especially young researchers. So we're going to try to be very concrete about how and what they should be working on and how they could do it.
Love it. I love it. Alvaro?
I would say, I mean, there's a lot that can be said here. First, a very cliched answer, but it's very true, and it's something I learned personally the hard way, is that you have to find a research area that you are passionate about. And what that means is you find a research area where you don't mind reading papers on the weekends, you don't mind reading papers on holidays, you don't mind running experiments. That shouldn't feel so much like a chore or a drag. It should be something that is, you know, exciting and rewarding to you. Once you have found that, you know you're in the broad area where you should focus your career on. Second thing, be wary of hype. By the time something becomes very hyped, it's a saturated market. It can cloud your vision for what the fundamental new discoveries might be. And finally, make sure you understand the distinction between research and engineering. These are two very different roles. Some people think they want to do science, but really they want to do engineering, and vice versa. So you have to really understand which of those two directions you want to focus on. Those would be my 3 key points.
That's great. Trung.
For me, I just want to share with them my personal experience. I was trained as a traditional electrical engineer, but later on, I followed the direction of money. I got a job at NASA where we start doing robotic and AI. So that's how I got into AI. And then I keep on, when I changed direction to academic, I got research funding to support me doing research on AI. That's how I went with AI and now with the FAA through job. So we will talk to them, highlight some of the work that we need at the FAA and try to tell them that we do have some internship at the FAA, that we do pay some stipend to entice them to join the FAA, and they will get involved with some specific projects that will get them to see more in detail of what is AI and what we're looking for. So what I like to share with them is get involved, but get paid for the involvement. That is important.
That's great. Oh my gosh. This is going to end our time here at this panel. Excellent, guys. I think we had a great time. I learned a lot. I hope everyone on the phone learned a lot. And those answers, the questions really are going to give us a lot of insight so we can make some really good decisions on directions we may want to invest in or go moving forward. So thank you again for your participation. We look forward to your continued participation. We're going to take a quick break here, and we're going to take a break from 1:50 to 2 p.m. Eastern. So once we're back at 2 p.m., Derek Morgan's going to lead us in a technical session that's focused on AI risk assessment and mitigation. So again, thank you all so much, and thank the panelists so much for being here today. And we look forward to seeing you guys in about 10 minutes. Thank you.
Thank you.
Thank you.
Thank you, Taylor.
Thanks.
Good afternoon and good morning to you way out west. This is Derek Morgan with Haas. And as we get prepped here for the next session, I'd like to ask Dr. Atkins, Dr. Koopman, and Dr. Zhu, if you would please put your cameras on and turn on your mics. Let's just do a quick check.
There we go. This is Phil, microphone test.
Wonderful. I can hear
Hey.
you and see you, Phil.
Great.
Hey, Ella Atkins, I'm here.
Hey, Dr. Atkins, I can hear you and see you.
Hi, Derek. This is Chi.
Ah, wonderful. Chi, thank you. I can see and hear you as well. Looks like I lost my camera, so we'll see if we can get it back. Perfect timing to have a technical glitch. How are you all seeing my camera? It looks really wobbly to me.
I don't see you.
Okay, that explains it.
Yeah,
All
I'm
right.
not seeing you at all.
Okay, so I'm going to go off camera and see if it'll fix itself. But thank you both, excuse me, thank you three for joining. And just want to confirm that each of you will share your presentation material. You guys ready? Okay. All right, wonderful. So we'll start off with Dr. Atkins and then go over to Dr. Koopman, and Dr. Zhu, you'll round us out as we get started here momentarily. Thank you.
And to be clear, this is 20-minute slots, more or less 15 presentation, 5 Q&A, correct?
Yeah, that's exactly right.
Will you be able to moderate the questions for us so we're not trying to watch stuff fly by while we're presenting?
Yes, yes. We have a few folks helping out with that, and we're going to do our level best.
So somebody will feed me questions. I can do that.
All right, wonderful.
Thanks. Just asking all the obvious ways I've seen it go wrong in other venues.
All right. And then we do have a couple of poll questions sprinkled in between the presentations. So we'll also need to make sure that we keep time for that. Okay, and we will give it another minute here for those of you who are returning from break. We do have our technical session on AI risk coming up, and my name is Derek Morgan. I'm with I'm a detailee from the FAA with Haas, and we'll get started here momentarily. And I apologize, I'm not on camera. My camera decided it wanted to flake out. So we'll get started here momentarily. All right. Well, hey, I tell you what, just let's go ahead and get going. And Dr. Atkins, if you wouldn't mind, go ahead and sharing your material while I introduce our panelists. So it is my privilege to welcome our three distinguished panelists for the AI Risk Assessment and Mitigation session. First up this morning, if you're way out on the West Coast. And our panelists come from three different universities. Dr. Ella Atkins is going to kick us off. Dr. Atkins is the Fred Durham Professor and Head of the Aerospace and Ocean Engineering Department at Virginia Tech. Followed by Dr. Atkins will be Philip Koopman. Professor Koopman joins us today from the Department of Electrical and Computer Engineering at Carnegie Mellon University. And Dr. Ji Zhu is an associate professor for the Department of Electrical and Computer Engineering at Northwestern University. We thank all of you for joining us today. And we've got a lot of information to pack into a pretty short period of time. So Dr. Atkins, why don't you get us going?
Sure. Can you guys see my screen okay?
I think now that, yeah, give it another try.
Can you see my screen now? No, you can't see it?
Nope, not yet.
Okay, it's been sharing for quite some time.
You might want to restart that.
again.
I think, yeah, we had to drop the previous chart. So
Okay.
okay, there we go.
Okay, so you should see my whole screen. And I can't tell whether you're seeing things or not. I'm going to put duplicate slideshow. All right, let me ask again. Are you seeing my screen now?
That is it. We can see it.
Awesome. And sorry for the April date, but it's actually May, I'm pretty sure. So to get things started, what are we doing in sensing, autonomy, and machine learning? And my focus is going to be on advanced air mobility. But advanced air mobility has small unmanned aircraft, air taxis, and everything in between as subsets of that. So when I say AAM, I really mean all of the aviation of the future that is not passenger carrying large transport operations, military, and so on. For sensing, these aircraft are going to fly close to the ground, so we need better maps and better real-time perception. Vision, LiDAR, radar, and other sensors have a lot of data coming out, so a lot of the application of AI is in understanding what those data streams are telling us quickly. Autonomy in the decision-making sort is really initially to help the pilots understand in a simplified vehicle operations sense what the state of the system is, the environment, and how to make decisions. And then also for very kind of boring things, we need to do things like run checklists and just fly the plane with an autopilot that might not be done with the human pilot, especially when the human pilot migrates off board. Now, one of the things that I think is considered the highest risk of AI and indeed autonomy for aviation of the future is what happens when the person is no longer on board, yet there are still people on board. These are passengers with no training to be pilots or otherwise operate the aircraft. Well, what that really means is that unless you trust your data link and a human pilot on the ground to make decisions where they aren't actually involved by being on the aircraft, the autonomy, it has to do it. Where the AI will come in particular, is in handling anomalies, things that would not normally be in the main line of code that is dealt with by running checklists and a nominal autopilot. And we actually need also better interfaces with people who don't have a lot of training. We want to have explainable AI or XAI that allows a more natural language interface to be used. And then the question, if you guys out there use ChatGPT regularly, you always wonder if it's right. And so I find myself always double checking, even if the answer seems satisfying. But then we also have a lot of backing of physics-based models, existing software, rule-based systems, and so on, that will give us that kind of trusted base. And so the idea with the AI and ML to minimize risk is that we only use it where it's needed, not replacing things that already work well today. Data link is going to be essential for the safety critical information. All right, so now the more provocative slide. What are we afraid to deploy? We have the assumption that the risk is so high if we deploy it that we shouldn't even do it right now. And this is a challenge because a lot of the risk is not accurate. So if you're in human factors, the phrase trust calibration is often used. The calibration of trust can go either way based on what someone thinks. It's usually not based on the quantitative statistics. Now, the people at this meeting probably know the safety statistics and can say, I think this is risky because I've calculated the value, and that's awesome. But a lot of people trust or don't trust just based on their first thought as opposed to this data. Well, right now in aviation, there are a lot of things that we don't have that maybe we should. So first on this list, machine learning based perception. If we have these data feeds that are coming in that can augment situational awareness, whether it's for a pilot or for software, we need to present this information. So we're getting to the point where the machine learning itself is what I'll call superhuman, meaning that it's able to run faster and present, in some cases, more accurate analysis of these very dense data streams than a person using their eyes might be able to do. Adaptive control has been around for 40 plus years, and it's still not certified to fly, even though it has been shown time and time again to be able to deal with things like structural failure and control surface jam, et cetera, cases that are very difficult for a human to figure out in real time. Data link, and then pilot override systems. We have some pilot override for things like flight envelope protection, runway overrun, but not in a more general sense. So why have you been looking at this Japan Airlines burning plane on the right-hand side, you probably are thinking. Well, it was very interesting. This happened because there was not clear communication between the Japan Airlines, between the Coast Guard plane that this Japan Airlines plane did not see and landed on top of, and air traffic control. From what I heard, and you guys may know a little more about this than me, but the remedies were to have more visible markings and clearer language in air traffic control to make sure that there could not be misinterpretation of a cleared to the active runway instruction. The thing that was interesting is that there was no mention in reports that I've seen of having even a data link that would say, hey, you can't cross this line, you're not cleared. And that would not be voice-based, it would not be XAI or even AI. This would just be another safety check, a watchdog of sorts in the background. The risk of having those types of watchdogs are that they might activate inappropriately. But in this case, a watchdog that says don't go onto the active runway would fail safe. The plane might not go onto the runway even if it was cleared when that watchdog failed, but there would be no collision, no fire, no loss of life. So what do we have to do in sensing? Well, there's a lot to do in sensing, and this is a nice little graphic of AirSim with Unreal Engine showing sensing from onboard simulated LiDAR, where this aircraft needs to land and is looking for landing sites on rooftops. In order to estimate state, we have some version of GPS or GNSS, usually an air data system, inertial measurement unit, and then ground-based systems like the instrument landing system that allow us to figure out what's going on. And then we also have radar and ADS-B to do things like track air traffic. We're increasingly getting for onboard sensing vision-based systems for runway, vertiport approach identification, and maps that are generated based on crowdsourcing, not only from specific geographic satellite and aircraft data that is calculated specifically for the purpose of building maps. So I'm not going to focus on this video, I'm going to go on, but there are a lot of methods out there for taking point clouds and RGB images, pipelining them through machine learning software to get very accurate real-time maps of the surroundings and deal with them, whether it's in this case having the quad rotor find a clear spot to land or navigating through an environment that has obstacles in it. One of the things that really is surprisingly in need of update are the vertical obstacle maps that we see in aviation. You see on the right here an aircraft that didn't know this vertical tower was here, obviously, and ran into it a couple of years ago. So if you think about vertical obstacles and you think about how they're mapped, in traditional aviation, we fly above all of them. We see them on the map, we stay well clear, we don't worry about them, and of course, they're accurately mapped as much as we need to know for approach and departure, but to runways, but that's about it. So if you have aircraft that for whatever reason are flying unusually low for things like agriculture applications, or in particular rotorcraft that tend to fly low on their missions, we have obstacle and wire strikes that happen on too regular a frequency. Now, it's interesting because these maps are really quite inaccurate. So some of the work that you could do to help these maps be more accurate and better updated, because we have a lot of infrastructure that is still being deployed month to month, is to actually have every aircraft that flies take data, process it, build vertical structure maps correlate things like towers to give you power line inference, and then have either overlays for pilots that you see with the circle and the rectangle on the upper right, or to have feeds into the automation software that's planning and following the routes to assure clearance if you have an automated system. Now, what's the risk of this? Well, the risk is that the data is either wrong or the processing of that data has given results that are wrong. So if a structure is there, but the data doesn't say it is, then the helicopter will go flying at full speed and potentially crash by hitting that obstacle. If you have a false positive, then you'll have your vehicle maneuvering around ghost towers. That is not unsafe. It's just inconvenient to go maneuvering around ghost towers. Obviously, it's unsafe to have the false negative or misdetection where you actually hit the tower. One of the reasons that this is imperative to put into these systems is because if you add the map that we have now to this increasingly accurate set of data, we're going to do better. Right now, if we just use the map and the limited accuracy of that map and the potential that it's out of date, we're going to have more misdetections because we're not able to see these towers. So even though there is risk in this form of sensor-based machine learning being deployed in the safety critical system of either overlaying displays for pilots or having autonomous collision avoidance, it's better than not doing it at all. In terms of autonomy, and when I say autonomy here, I mean more decision making. If we look at how a pilot deals with autonomy, we have aviate, navigate, communicate. When you look at emergency landing, that gets translated into specific things like figuring out what the airplane can still do following damage or degradation of systems, choose a landing site, planning path to that site, and execute it. We can do the same thing. And in terms of machine learning, this first slide is showing what a very simple algorithm could have been to help Sully in this case, where no one died, and that's awesome, return to LaGuardia and to feed that information by data link back to air traffic control as soon as possible. Now, this would be very low risk because there's no AI, there's no machine learning in this type of system. It just needs to be put into the system. So we have systems right now like Garmin Autoland that do this, but they're not part of the entire network that also is communicated air traffic control, which is the second piece of the puzzle that needs to be put in. What is a little higher risk, though, is, again, this notion of finding where you're going to land as part of the landing itself. The risk being that if your data is processed incorrectly, that you're not going to get a valid spot to land. One of the opportunities that we have in the future is to exploit the vehicle-to-vehicle or V2V link that we're increasingly deploying in cars on roads in a way that allows the aircraft in the sky to network with the cars on the road. And what that would allow to happen is if you have emergency landings like you're seeing at the right-hand side, is something that happened in 2017, and the pilot actually got out of the airplane and was safe. That allows things like coordination. Now, this is a very low probability occurrence, but it's still something that happens more often in general aviation in particular than you might think. I'm going to keep going because 15 minutes goes awfully fast. And for some reason, my computer, there we go, is not showing. Okay, so if I think about machine learning for advanced air mobility more generally, my screen has crashed. There we are. What might we want to do in general for air traffic management and advanced air mobility? Well, in air traffic controller support, there's conflict detection, conflict resolution, and both. And these are all safety critical functions. So the risk of having machine learning or AI in this loop are that, of course, a conflict could be missed or resolved incorrectly. The advantage would be that there might be extra support for the air traffic controllers in finding conflicts that were missed or resolutions that would not have actually resolved the problem. Operations support, Maintenance scheduling is already done, and increasingly we're using machine learning in data processing for that. Prognostics and diagnostics, even in real time, can help us understand whether it's on the ground with air traffic control facilities and radars or in the sky with the aircraft, what might be going wrong, and deal with that before it actually does. With all of these, in terms of the risk of the AI, you always ask the question, is it right? We like this notion that we can prove correctness of everything, yet we have this tension between provably correct but rigid and flexible, but it could be wrong. And the more data we have, the more dynamicism we have, and the more capabilities that we deploy and test carefully in controlled ways when possible, the more able we will be to actually reduce risk as we deploy new products and new operations such as AAM in the future. This is my last slide that I need to show before I run out of time. And this really is getting specifically at the FAA's challenge in certifying AI and machine learning. And this slide focuses on machine learning in particular. The thing that's scary about machine learning is obviously it can change the parameters, change the models, change the logic even once a system is flying, if it's allowed to do that. What we're able to do right now in aviation is to apply machine learning only before certification. That's this first bullet point that says BC, that's before certification. So if you actually only allow machine learning before certification, the product that is certified is actually neither AI nor machine learning. It is logic, usually a set of rules that have data associated with them that is static, that can then be used. Those might be very useful, like with ACAS-X, a collision avoidance system, but they're not machine learning once they are certified and deployed, because that's not allowed. The next stage in allowing machine learning to be used for aviation in certified products is to not allow machine learning in real time, but allow it when you're analyzing previous data in an offline mode. What that will allow, which is huge, is day to day, week to week, the machine learning could actually be run with a combination of domain experts and users plus machine learning experts to watch and monitor and check adaptations that happen. But if it's allowed in this offline mode, you would not have to recertify the product. The machine learning could happen, and there could be an updated product available that is not recertified. The third is to allow real-time certification. In short, the reason to allow real-time machine learning. In short, the reason to allow real-time machine learning is to adapt when traffic, aircraft performance, and the environment do not do what you expect, and there is no backup. And especially if we have passenger carrying air taxis in AAM that do not have expert pilots on board. We need this adaptation because there will be no clever, experienced human to save the day when things go wrong that the rigid certified products cannot handle. Now, the risk is obvious here. If this machine learning adapts in real time incorrectly, a crash can occur. But the alternative is to not have a product that is able to adapt, even in some way like to adjust the model through system identification or adaptive control that would recover when something happens that changes the performance of the aircraft. All right, I'm going to stop there with a video. I don't know if I have time for any questions, but I'll let this video play as the questions might come up. This is a netted facility demonstration of what I think is the first user-guided cooperative payload transport, meaning we have 5 drones tethered to a common payload, and the way that the payload is being guided once it takes off the ground is by a human pushing on the payload, and the force is sensed, and that drives it.
Thank you, Dr. Atkins. What an interesting discussion. And we're going to make time for one question for you. And then right after this, we'll get into our next poll question. But, you know, the emergency landing, you know, the forced landing scenario does beg the question about you know, proper performance, especially during failure conditions. So from your perspective, you know, what's the roadmap of sort of contingency system development in the near future to address, you know, uncertainty in flight operations, yet taking advantage of what we can in a safe way as the technology becomes available?
So one of the things, I've been studying this problem for 25 years now. And one of the things that I learned early on as a hard lesson is that emergency or contingency management automation is not going to sell until there's demand by the customers, by the airlines, by the equipment manufacturers, by whoever it is that sees a need for it. I think we're in a new era now with AAM where we know we need it, and it's a question of how. There's the easy cases that you can model in advance. For example, losing one or more motors, or having a control surface jam, and a number of other failures, which include failures of certain sensors and medical emergencies, which don't change the performance of the aircraft, but you need to get down really soon. We know how to do that today. We have models that we can store in a database, and we can make emergency landing plans. Something that my group has been working on with NASA Langley is this architecture called ACLM, the Assured Contingency Landing Management Architecture. And what that allows is before flight, you can build hundreds, if not thousands, of flight plans that are ready to go for every segment of your flight that you're planning to land. This is the scaled up version for a computer of the notion of having an alternate landing plan. A human could never calculate manually 1,000 flight plans and be ready to execute them, but a computer can do that quite easily as part of its pre-flight. So what we would hope there is that instead of having a situation where you have to struggle with your computer to choose a landing site and calculate a real-time flight plan after something happened, you store those plans in advance. If you fly the same route day to day, you don't even have to recompute them every day, and then you can retrieve them and use them as the situation calls for. The second part of that is really to have a better relationship with air traffic management. That, I think, is going to be the harder one, where when you have an aircraft that needs to make an emergency landing, there's two questions. One is, what path does it need to follow to be safest, all the way down to the ground, to the landing site? The second one is, how do you make sure it doesn't hit any other aircraft on the way down? The US Airways case in New York, there were two reasons that Sully couldn't come back to LaGuardia. One is he didn't have that geometric planning tool that gave him the confidence that that math would work out to reach the runway, even though he was a glider. That one is solved by systems like Garmin Autoland, and what many people have done with gliding aircraft in the literature. The second one is that with voice-based air traffic control, there was a significant delay between when the emergency happened and when air traffic control actually understood that this aircraft had lost both of its engines. And that amount of time was sufficient that the plane couldn't get back. So that data link is really a critical part of being able, especially in densely populated urban airspace, to manage the contingencies in a way that is best for that aircraft that is declared an emergency.
Wonderful. Thank you for those insights, Dr. Atkins. Very much appreciated. I suspect I'll be calling you in the not too distant future as a follow-up. So let's move on to Dr. Koopman. Dr. Koopman, please take it away.
Okay, you should be hearing me and seeing my screen. How are we doing?
Both are good.
Okay, let me dive in. I'm Phil Koopman. I'm a professor at Carnegie Mellon University. I've been working on self-driving car safety for more than 25 years, getting close to 30 at this point. And more recently, I've written a couple books on the topic about UL 4600, which is a system-level safety standard for autonomous cars. and trucks, and also how safe is safe enough, which gets into the, oh, people say they want it to be as safe as a human driver, but they have no idea how hard that is usually. So what I'm going to do in my small amount of time here is I'm going to go kind of fast, and I'll give you a pointer at the end for the longer, more fulsome versions of all these. But I'm going to talk about 6 challenges in autonomous vehicle assessment, because fully autonomous cars are out on the roads and trucks are out on the roads, sometimes with human supervision, sometimes not. And we've learned an awful lot about what people thought and what went right and what went wrong and the surprises. So I want to go over the dimensions to what safety means. And I think part of what we have, one of the earlier questions was, are the AI people really talking to the safety people? And I've been in the workshops where that tries to happen. And one of the biggest gulfs is people say the word safe and they mean completely different things and don't even realize it. So I want to go over, take this talk through the lens of there's different ways to look at what safe even means. And if you don't know what safe means, if you can't agree on safe means, then I have no idea how you're going to get AI safety that means anything at all. So this is a first step. And I'll just talk about these 6 topics. I won't spend the time now to list them. First, brute force road testing. Initially, people said, and then the safety folks knew this wasn't going to work, but the people building technology said, well, we're just going to drive around, and if we drive along long enough without a crash, we'll know it's perfect. And the numbers just don't work. You have ballpark 100 million miles per fatality in the US. It goes up, it goes down. That's a long-term average. We know human drivers can do about that. And if you want to get 95% confidence, you're testing 3 times longer with no mishaps, but you probably will have one. By the time you're done, it's probably 1 billion miles of testing to get statistical significance under very favorable statistical assumptions, which are probably not true. But what does that mean? That's like 50 round trips on every road in the world with fewer than 10 fatalities. Okay. Where are we now? Well, we're at 7 to 10 million miles, 100x more miles to go. You have companies claiming we're already saving lives, and they're a factor of 100 out from knowing if they're actually safer than human drivers or not. They've saved maybe 1/10 of a life or something like that. And if you have heavy tail events, there's a long talk I can do about this, but I'll give you the very short version. That optimistic math assumes independent arrivals with a light tail, meaning that the rare events are actually kind of rare. There's a lot of reason to believe that there's a very large number of rare events, and the area under the curve out at the very rare events is very substantial. And this is why you're seeing companies perhaps taking 10 years and still running into stuff they never saw before. So it's very challenging. The takeaway is, whether you believe it's heavy tail or not, brute force testing is never going to prove you're safe, because it's just going to take too long. Now, aircraft, you don't fly around till the wings fall off and then decide whether it's okay to put passengers on or not. You do something smarter than this, and we're going to have to do something smarter than this for self-driving cars. So raw brute force accumulation of miles is not going to work for assessment. That may seem obvious after I do the slide, but believe me, it has to be said. Now, what is the industry doing instead? Well, what they're doing, and I'm going to call it assessment, but it's more of a PR attempt, is they're saying humans are terrible drivers. They drink and drive. They're distracted. They're drive drowsy. And because robots don't do those, of course, they'll be safer. The takeaway from this overhyped ad is, well, those 43,000 Americans would not be dead if all the robots were driving, because robots don't make stupid human mistakes. Well, human drivers are actually pretty impressive. 1 fatality per 100 million miles is actually a pretty favorable rate. The number of fatalities is simply because of the huge number of miles. But the other thing that we found out when these went on the road is, in fact, we're told in this ad, well, robots don't make stupid mistakes, is clearly the takeaway. Well, it turns out robots do make stupid mistakes. Here's a robotaxi that rear-ended a city bus because it had not been trained properly on articulated buses with a joint in the middle. And the bottom line is it had a software defect that caused it to ignore the back half of the bus and decide it's far enough behind the front end of the bus and ran into the back half, even though there was no extenuating circumstance. Turns out self-driving cars, robotaxis, have software defects. And software defects lead to crashes. So they may not drive drunk. They don't have human errors because there's no person driving, but they have robot errors. Here's another one that's more recent. Another robotaxi crashes into a telephone pole. The company is being very quiet. They're really not talking about this at all. But I can assure you if they're an extenuating circumstance, we have heard from them about it now. There also have been more severe crashes. There was an injury crash with a collision with a fire truck because the robotaxi failed to yield to the fire truck on a cross street. And there was a highly publicized pedestrian dragging mishap. The victim there did survive, but with very severe injuries. So we're seeing that saying, well, these things are robots, so you don't have to worry about safety because they won't make stupid mistakes. So don't even bother, it's just let's go on the road. That is not a good assessment strategy either. And from a public messaging point of view, in a regulation point of view, we also saw these companies say, just let us do our thing because we're busy saving lives here. It's so obviously safer. Don't regulate us. You're getting in the way. You're killing people by slowing us down. And the data isn't there to support this, part one, but part two, it turns out to be a PR disaster for the industry. So I would caution other industries from avoiding saying we're doing this to save lives, because it takes hundreds of millions of miles to prove you're saving lives, and it only takes a few million miles to get bad pictures in the press that tell you maybe it's not as safe as we thought. So basically that messaging strategy is all downside and no upside. You should have a smarter messaging strategy than that. And there are such, but that's a different discussion. So continuing on, what's a core problem? The heavy tail is a core problem, but another core problem for assessment is that in automotive, you have the traditional safety engineering V model. This is used in a lot of industries. And what you do is you trace requirements to implementation, and the testing validates the engineering process. Now, a really key thing here that is not necessarily obvious from the way a lot of engineering is taught is the testing does not prove you're safe. The testing can't prove you're safe. I already gave you the numbers. Testing won't prove you're safe. It takes too much testing. So what's this test doing? The testing has to trace back to the left side of the V to mean anything. And what the testing is doing is, and I'm intentionally using some Bayesian statistics terminology here, the left side of the V sets up a prior expectation that you're safe because you followed your procedures and safety standards and best practices. And the testing is not there to prove you're safe. The testing is there to provide evidence supporting your Bayesian prior assumption that you're safe is justified by a much smaller amount of data. So the testing isn't there to test safety. The testing isn't there to find bugs. Well, it's there to find bugs, but the bugs aren't fix the bug and you're fine. The bug is, wow, every bug means my engineering process failed, so I've lost confidence in the integrity of my engineering. And that mindset is really subtle, but it's super important because machine learning breaks it. With machine learning, there's this magic black box process that goes from something pretty high level, you train on a bunch of data, you get an implementation out, and it's no longer possible to say, all right, here's the requirement, here's a detailed requirement, here's the line of code, here's the unit test. You lose that traceability. So even you'd say, well, I know my car's supposed to do something. Why would you believe it does what you think and doesn't do what you don't think it should do? Because you don't have this traceability. That leads you into brute force testing. And sure, you can use simulation, but how do you know the simulation has all the rare events that were happening at every 50 million miles if you only have 10 million miles of testing? So this is a very thorny problem. There are ways around it, but this is why the current safety critical approaches break on a technical basis, is because you lose the traceability from the left to the right-hand side of the V. Now, there are a bunch of standards. One of the things you can do to set a prior expectation of safety is to be following your industry safety standards. Now, it may be surprising, perhaps even shocking to people in other industries, but unlike aviation, unlike rail, unlike all these other industries I've had safety experience with, I've read so many different safety standards, automotive is not required to follow their own safety standards. And some of the robotaxi companies have gone on record saying the standards don't work for them because they're not a good fit. Now that's been tempered slightly, but their going in expectation is no, we don't need safety standards. We got this, trust us because we're smart. And that's having problems out on the road. So there are vehicle safety standards, FMVSS, and there's NCAP. So this applies to all cars. This is, and I know I'm simplifying, but do your headlights work? Do your brakes work? This is normal car functions. You have to have a cybersecurity standard. That standard's out. There's functional safety, and I'm not even going to try and say the numbers speaking this quickly, but the numbers are all out there. Functional safety is if there's a fault inside the unit, does the system fail safe, to very simplify it. There's things about dynamic driving function, which is, hey, you know, radars aren't perfect, LiDARs aren't perfect, and maybe we're going to see something we didn't expect. How do you plan to do with that? And there's system level safety standards. ANSI UL 4600 is out. ISO TS 5083 will be out soon. And those are talking about things beyond just driving. And I have a slide coming up on that, so I'll go over it more there. One of the concepts being used is, instead of saying there's a rule book like a building code, use wood this thick to give the right amount of structure. You know, don't tell us how to build it. Tell us how to build a safety case that argues we got it right. And ANSI UL 4600 is designed around that, and that's currently a trend that the self-driving car companies the autonomy companies are looking at, how to have a way to assess the safety case. So one of the right takeaways I'd recommend is look at assessing the safety case rather than assessing the product based on particular rules, and that's what 4600 does. Right now, these are the only safety standards required. The rest are completely optional, and I don't know of any company who says publicly they will follow them all. Some of them do some of it, but you know, this is not a standards conformance industry right now. There is a US DOT put out an advance notice of proposed rulemaking in December 2020 saying, what say we make the industry follow all these? And that's been gathering dust. So US DOT ought to really consider pushing that forward. Now, there's more to safety than just driving. Cute kid, is this car safe to move? No, the kid's not strapped in, right? Okay, well, there's this thought that, well, if I can get my robotaxi, if I have a computer driver and the computer driver can drive down the street and not hit things and follow all the road rules and get out of the way of fire trucks and do all these things, I'm good to go for a robotaxi. And that's simply not true, because drivers do more than drive. Who's making sure the kid's buckled in? Who's making sure that, and if it's not a kid, let's say it's an adult who's drunk and the drunk's passed out in the back of the robotaxi, who's dealing with that? You know, probably not a computer driver that just knows how to move around. Who's detecting and managing equipment faults? What happens if the system gets thrown out of its operational design domain? You're in Vegas and it starts snowing while you're moving. Does the car know how to deal with that? What if there's a crash? One of the pedestrian dragging mishap, a lot of that had to do with bad post-crash response. The computer driver was programmed to do something that was inappropriate for the circumstance. So it's a lot more than driving. What about lifecycle management? Sure, you have security, but somebody has to make sure the sensors are calibrated and maintained. And how safety critical are the cloud support services? There's a lot more to this than just, can I get a driver that drives down the road? And the system safety standards address this. But just realize, just because you have something that knows how to drive doesn't mean you have something that's going to be safe for all the things that really need to happen to take the human driver out of the vehicle. Right now, the companies have large remote support staffs, and that's not going to scale up. So they're still working on that. The last substantive slide, let me talk about what safe means. What you'll hear people say, well, as long as we're safer than a human driver, then it's fine. And that book I showed you, the Safe Enough book, started with, well, what do you mean by safer than human? And it depends on what zip code they're in, what age they're in, what kind of car they're driving, what kind of weather. It gets really complicated in a hurry. And then if you start asking the next set of questions, you ask, well, okay, now this is a completely hypothetical thought experiment. I'm not saying any robotaxi company would do this, but what if the number of fatalities cuts in half? Okay, so you're safer than a human driver, but the number of pedestrian fatalities doubles. That's going to be a problem for pedestrians, isn't it? So it turns out statistical gains on safety are not enough. You need a much more robust definition of what safety means to keep stakeholders happy. That's going to blow back on you if you end up with that kind of outcome. Now, would that happen? I mean, who knows? But it needs to be a design constraint that's taken into account and not have an unhappy surprise later when you find out you have this risk transfer on the vulnerable populations. You also have to avoid negligent computer driving. You should probably be holding computers to a human driver duty of care. So for example, if you find out that running through stop signs at 5 miles an hour you think is safer because you have less rear end crashes, you're breaking the law. And if you were to injure a pedestrian that you don't happen to see because your sensing is not perfect, you're basically, that could be negligent homicide or whatever the equivalent is in the state. And is that okay for a computer driver to take a chance on? And by the way, who goes to jail if it's a computer? You know, that kind of stuff you can't ignore anymore. You used to be able to ignore legal constraints in safety for the most part, because you could just heap that on the human driver and say it's not a technical problem. Guess what? There's no human driver. It becomes a technical problem. I would say you probably need to conform to industry safety standards, because that's the only way you're really going to get a robust idea that you were safe before you start doing deployment. And by the way, once you take the human driver out of the vehicle, or break the concept that there's a remote human with a steering wheel, which isn't going to work anyway, but once there's not a human driver who's in real time there every second, ready to take over in a fraction of a second, that's a deployment. That's not testing, that's a deployment. And the companies say, oh, we're testing without a driver. What they mean is we have an immature product that we're not sure is safe, but we're going to put it out on the road anyway and see what happens. And the folks who are in the cities where that's happening are not too happy about that situation. So ask what it means to deploy. And I would say if the human operator is not instantly responsible for safety, that's a deployment, and you should be very careful whether you allow that to happen. And there are a bunch of other ethical and equity considerations, things like the locality should have the ability to have some sort of control over this instead of it being imposed on them. And there has to be an accountability to the companies for harm. There's been a lot of state legislation which the net outcome is to make it really hard to go after the companies if they cause harm, and that's a problem. So when you say, oh, it's safe, if you haven't answered all these questions, you haven't really defined what safe means. There's a lot to it. It's more than just net statistical outcome. Okay, wrapping up, because I'm at my time. I've given you 6 different ways that you have to think about for assessment. If you want to assess safety, you have to define what safe means, and you probably have to consider all these things. And some of them are pretty substantive. Some of them are unsolved problems. If you want more YouTube video than you can possibly stand, go to that link, and most of these things have a whole keynote talk behind them, and have fun watching, but I'll stop here. And if I have time for questions, fine. And if we have to move on, that's fine too. Thank you.
Hey, thank you, Dr. Cutman. I think we're just going to try to make time for a question, and you know, there were a few, but let's go with the question about how developers or the industry can address overlapped or uncovered areas in safety standards. What are your thoughts on that?
Well, in the safety standards, to be clear.
Yes.
So those safety standards are pretty good at allowing you to know whether you got safety right. What they don't have necessarily, and I think 5083 is trying to address this a little more, but it's still draft. What they don't have is a recipe for how to get it right. And I think because no one's really sure how to get this right yet, and a lot of that knowledge is very proprietary. So I would say if you're going to assessment, don't worry about whether the standards have gaps on use this formula to get a good outcome. I would instead say, ask yourself how you can have high confidence that your assessment has an accurate result conclusion as to what the safety is. And don't make them do it a certain way. Ask, so you say you're safe, explain to me why I should believe you, where's your evidence? And then let each company fill in the gaps as they think makes sense. Because this is immature technology. We don't know the one true way to get safety. It's much more about having a reasonable story to tell, part one. And part two, by the way, UL 4600 requires field monitoring, because you're probably going to have a lot of uncertainty about how safe you really are. You'll deploy in good faith saying we're safe enough, but there's going to be a lot of assumptions that no one really knows if they're good assumptions. So I also want to hear your plan for field monitoring to see if those assumptions were correct or not, and what you can do about it when you find out one of them is wrong.
Wonderful. Thank you for those insights. We'll try to do our best to reply to the questions that we just don't get to here as we go on, if we can recover a little bit of time later on, everyone. But right now, we want to try to get in those poll questions. So we have a couple of poll questions before we have Dr. Zhu come up, and just would love everybody's participation. So let's bring those up now.
All right, so can you see my screen? I'm sharing the Mentimeter.
Yes.
Okay, great. Okay, so I have turned on the responses, And so now we are on to question 5, which is how effective are current risk mitigation strategies in minimizing the potential negative impacts of AI systems? And I'm going to set the timer for 1 minute. Okay, so as a reminder, your responses are anonymous. Fifteen more seconds. All right, so I guess I'm going to turn on the responses here. All right, so majority of the people think it's not too effective. So the strategies are not too effective in minimizing the negative impacts of AI systems. And I guess we are moving on to the next poll, right?
Yep,
I'll
question
keep this,
6.
yeah, question 6. All right, so question 6, I'm going to turn this on. And this is, how would you rate the academic community's understanding of the potential long-term risks posed by AI technologies? And so we'll set the timer again for 1 minute. So hopefully this time we'll get a number over 78. The last time we had 78 respondents. So as a reminder, your responses will remain anonymous. And all of your insights will be highly valuable. I'm hoping we clear the 78 mark. Okay, not quite. All right, so that's like an average rating. So I think yes. So with that, I think I will. I don't know if Derek, if you want to.
I've got it. So yeah, these are so insightful. It'd be really cool to explore these in more depth, even as we go. But in light of time, we want to make sure that we round out this session and hear from Dr. Zhu. If you'd like to bring up your charts, we'll turn it over to you.
All right, let me try to share my window.
And while he's doing that, I'll just give a thank you to everyone for participating in the poll questions. We want to get as much data as we can, so appreciate your effort in that regard. All right, over to you, Dr. Zhu.
You see my slides in full screen now?
Yes.
All right, great. Yeah, thanks, Ella and Phil for outlining already some of those major risks from AI. So I'll go a little bit into the technical side and some of the detail, a little bit into the details, in particular focusing on how do we analyze and potentially address the uncertainties in transportation systems, especially those related to AI risks. I'll use connected and automated vehicles as the example. Some of those, I think, challenges and messages, solutions could apply to other domains as well. So for vehicles, we all know the interact with a fairly complex physical environment at real time, and through nowadays quite sophisticated sensing and perception algorithms, almost all based on deep neural networks nowadays. And then there are also increasing interest in applying machine learning, especially neural network-based solutions for planning as well. And those machine learning algorithms will then be implemented on a software hardware platform. Now, the increasing usage of AI, especially the deep neural network-based solutions, they bring risks across system layers. So at the algorithm level, we have to deal with quite dynamic and uncertain environment. The neural networks are complex and their behavior is often hard to analyze and sometimes unpredictable. Then at the software hardware level, the software complexity has been increasing drastically over the last 1.5 decades or so. There's very intensive resource requirements right now on the hardware side, and also lead to quite complex force and software hardware levels and very tight timing constraints as well. So all those bring a variety of risks in safety, in security, in privacy, reliability, etc. So I'll focus mostly on the safety side, maybe a little bit into security. So fundamentally, a lot of those challenges and risks, they are brought by this variety of sort of uncertainties and disturbances in CVs. Those uncertainties are quite ubiquitous, right? If you think about it, the input inherently they are uncertain. And then you have a sense of noise due to hardware limitations, but also from environment interference and sometimes even sort of malicious attacks. And then with the limitation of the ML algorithms themselves with the training set, and so we all have errors in perception and potentially in planning and control as well. You may have a noise in actuation. And then when we implement those algorithms on software hardware platform during the execution, there will be unavoidably transient errors, soft errors, and a variety of disturbances as well. Then if we think about vehicle-to-vehicle or vehicle-to-infrastructure communications, those communications themselves are sort of susceptible to disruptions as well. So to analyze and address those uncertainties and potentially mitigate some of those risks. So I'll talk about from sort of try to answer 4 questions. I'll propose sort of 4 more general questions and talk about for each of those questions, some of the potential directions. So the first question is, I think the first thing we'll ask is under those uncertainties, actually, how do we even assess system safety, right? So there's obviously a lot of different works and from different angles trying to address this. I'll talk a little bit about how formal methods, formal verification tools have been developed to sort of address this problem, try to derive sort of what would be a safety margin, right, for the system under those uncertainties. In particular, here, as you can see, this is a very simple illustration of autonomous vehicle, where you have a physical plant where the vehicle will operate within a surrounding environment. And then through a variety of sensors, they will capture observation of the environment, right, and observation Y. That will go through your sensing and the perception module, which will generate an estimation of system state for the vehicle itself, right, from localization modules, but also for the surrounding environment. And then based on this estimation of system state, the planning and control module will try to generate a trajectory, hopefully safe, and then we'll apply the actuation signal to control the vehicle. Now, so the first problem we're looking at, right, is is one small problem in addressing the sort of whole sort of formal analysis of safety, which is how do we conduct end-to-end verification of system safety if there's some sort of input uncertainty, right, in the observation Y. So for instance, if we add a small delta Y into the observation, that will, after it goes through the sensing and perception module, will sort of lead to an error of the state estimation as well, delta X. Then the question is, right, will that delta X somehow lead to an unsafe system state? So this is actually can be sort of viewed as two very closely related problems. The first problem is a robustness certification problem. For instance, right, how do we, in this case, how do we, can we actually bound the state estimation error delta X after sensing and perception module, given some sort of a bounded input uncertainty delta Y? Then the second question is, right, if we do have a bounded system state estimation error delta X, how do we verify the system safety under the planning and control module? Right? So that's a system verification problem. So for the first problem, the robustness certification problem, it is mathematically what we call output range analysis problem. If you look at a perception neural network shown here, right, for its input Y, now the Y is not a single point in the input space, but rather given the uncertainty, we can view them as sort of a small compact set, right? Sort of view as a ball here. The mathematical problem is really after this small compact set of Y propagated through the deep neural network. Nowadays is typically a fairly large neural network. As the output, can we reason about what would be the bound, right, for the output X? Because now X is not a single point as well, but rather a set, right? And in many cases, a very accurate analysis of X is quite intractable. So in many cases, it's sort of over approximation of the X. Can we bound it? And there has been a lot of work in the literature trying to address this in the formal method community. The early approach used so-called interval relaxation to can view this as when you propagate this sort of a set of Y, go through the neurons, each neuron through its nonlinear activity functions, we approximate it just by the input interval and output interval. The challenge of this is a fairly efficient approach, but the challenge of this is usually after you propagate many layers at the output, the potential bound for X will become too loose, right? And not very useful for analysis. So there has been other approach of, for instance, using LP relaxation, trying to generate sort of a linear polytope to approximate those activation functions more accurately. That we can give you a tighter bound and then hopefully still make it relatively efficient. And then recently, we have also done some work trying to further improve the approximation accuracy by using divided the input space into multiple segments and use LP relaxation. So this is sort of a line of work that can give you some sort of bound at the output. Then once we have the bounded state estimation error X, right, as a perception output, now this becomes input for the planning and control module. And here the problem is really, can we reason about where the system go into some unsafe state, right? If we start from this initial set of possible X value. Because now again, given the uncertainty, the current state X is not a single value, but rather it's a bounded set. And this type of safety is what we call sort of reachability-based safety. And the mathematical problem is really in the finite horizon, can we reason about from this initial set X0, right? What the other states the system may arrive, can it avoid a predefined unsafe state, right? In the vehicle science, you don't want to collide with other vehicles, you don't want to drive off the road, and safely reach some target set. For this problem, this type of reachability analysis problem has also been studied quite extensively in the formal methods community. And there had been sort of a very good tools developed for traditional model-based control. where you would have sort of a model-based controller based on explicitly physical models, and we can reason about their reachability, the reachable states. More recently, with the increasing popularity of neural network-based control, people start looking at what if the controller is a neural network, right? In this case, we have recently done some work trying to using bursting polynomials to approximate this neural network with a polynomial. Right? Once we are able to do that, then we can leverage the existing tools for this reachability analysis for the traditional model-based control, where the controller is polynomial-based. And the advantage of this approach, we did this a few years ago. The advantage of this is using bursting polynomials. It applies to any Lipschitz continuous neural network, so not just ReLU networks. But the challenge here is the approach doesn't really exploit the internal neural network structure, and the error analysis requires sampling to the input space. So it doesn't really scale. So we were able to address systems with maybe with 5, 6 sort of free state variables, even with some sort of engineering improvement with GPU parallelization and all that. So more recently, we started looking at another direction where we sort of combine Taylor models and bursting polynomials and with some of the other techniques to improve the scalability. So this most recent work with this new tool called Polar and Polar Express, we're able to address systems with anywhere between maybe 15 to 20 free state variables in some cases. So that has been a big improvement. But still, it's a long way to go compared to the real practical system. So now if we look at those two paths, if we combine this robust analysis, giving this input is sort of uncertainty delta y, we can analyze the boundary delta x, then we do the safety verification. That's sort of close the loop. We can actually derive a safe margin for the delta y. So as long as the delta y within certain bound, we know the system is safe. However, this sort of works in principle, but it's still there are a lot of open challenges, mostly on scalability and efficiency. So this has been a challenge for formal method for many years. Right now, for the work we have been done, we are only be able to address quite a limited neural network size. So the input perception neural network can address up to tens of thousands of neurons, which is way smaller than the sort of the ones in practice. And also it takes quite some time to run. So both the robustness certification and the safety verification takes hours of the time, even for those smaller neural networks. And the end result of that is we are only able to sort of safely verify fairly small safe margin. So not really useful in practice at this moment. So there are some directions to address that. We are exploring that, for instance, using probabilistic-based approach and trying to break the loop with analysis of global robustness, etc. Right. So those are some of the directions on the formal method itself. But before we have those, right, what are some of the ways? I'll quickly go through sort of 3 directions. So one is if we find during runtime the safe margin have been violated, our estimation of the uncertainty is too high. Now, what can we do? One possibility is to conduct runtime adaptations. So, for instance, with runtime adaptations, hopefully, we can either sort of reduce the uncertainty, or in some cases, actually, when we explore the potential of switching among multiple controllers, right? So some of the controllers in their design, they may have better performance. Some of them may be more robust to uncertainty. So they may have a larger sort of safety margin for uncertainties. In that case, then one potential solution is you can design an adapter to intelligently switching among different controllers, including traditional model-based ones, which may be more robust to some of the uncertainties, and also the neural network-based ones. And to accommodate those changing of the environment and try to get within safety margin. The key here is actually to make sure not only we are safe before and after adaptation, but also actually while we're doing the switching, the system always we sort of maintain within a safety sort of region. There are other potential adaptation techniques. For instance, if you find that right the perception uncertainty is too high, then one potential simple solution is to increase the sort of sampling frequency and try to reduce some of those uncertainties. If it's those sort of allegorical epistemic uncertainties or model uncertainties. Now, another question we're asking is, right, can we actually, besides runtime adaptation, reduce uncertainties from some other angle? Now, one of the possible
to test how I am submitted.
One of the possible ways is to leverage V2V or V2 infrastructure communications to reduce uncertainties. So a simple example is a hard case actually in autonomous driving is unprotected left turn, right? So when here is the example, the vehicle C1 will try to make an unprotected left turn, then you have a vehicle, incoming vehicle C2 coming at you. And C1 may have a neural network-based planner that will make decisions based on its own state, but also its estimation of C2 state, like C2 location, speed, and acceleration. Among those, location speed usually you can estimate fairly accurately, but the acceleration is something fairly difficult to estimate very accurately because that's the intention of the C2. Now, in principle, we can try to verify C1's planner, use some of the techniques right I was mentioning. But if the estimation of C2 state, especially on its acceleration, is if that uncertainty is too high, then it would be very difficult, almost impossible to verify the safety of C1's planner. So in this case, if we leverage the vehicle-to-vehicle communication, if C2 can share right, its state and intention with C1, that potentially can reduce uncertainty and facilitate the safety verification. But of course, this also opens to its own problem. V2X communication themselves is vulnerable to malicious attacks and communication disturbances. So there's sort of two sides of this. So the last potential sort of direction to address this is, can we actually improve, right, or increase the safety margin for those learning-based components, for those neural network-based components? So one direction we have looked at a little bit is safety-driven learning. So basically, while we are learning the those neural networks for perception, for planning, for control, we're trying to improve their robustness with respect to the uncertainties. We have done some work both for the perception module, where the focus was more on addressing a variety of sort of adversarial attacks to the perception and the prediction module, and also for the planning module as well, where we looked into can we learn a safe reinforcement learning-based controller. And the key idea there is what we have found is it's really important to start thinking about verification and at least the verifiability of the system from the very beginning. So when we are conducting reinforcement learning, not only are we learning a policy, but we are also trying to generate some sort of safety barrier. And we found this is quite important. This consideration of joint learning and verification from the very beginning of the system design, in many cases, can help us find much safer design. Don't wait until right we already have the design and try to verify the system. Another lesson we learned is it's often needed to go beyond just safety driven. So a lot of times, I think a lot of methods is called safety driven, where we use the right accumulated cost function to penalize the potential safety violation. That in many cases cannot lead to a sort of a safe design where system can remain safe at every moment, every state. The last thing is, given the inherent uncertainty of the environment, I think many of those safety assured learning problems, we probably have to define safety in probability terms. And at the end of the day, the system level safety matrix will be evaluated based on probability terms anyway, right? So at the very beginning, I think it's beneficial to to develop new technologies where we can actually reason about safety in a probability sense. All right, so that's a quick summary. I think we've been looking at this, some of those sort of AI-induced safety risks and how do we try to mitigate them, centering around uncertainties. And so those are some of the direction we have been looking at, but almost for each of those questions, right? How do we assess system safety? What if the system uncertainties are outside of safety margin? How do we reduce uncertainties and how do we increase the safety margin? For each of there are many directions to address them, right? So I'll be very happy to chat more if you're interested. Thank you.
So many questions from everyone, and especially from that last discussion, especially building upon some of the previous conversation there. But let's pick one, Dr. Zhu. So there was one that was also of interest to me, but it says, can you please explain your thoughts for how the switch between controllers would have a smooth state transition? How would you avoid dithering in that concept?
Yeah, that's a good question. So yes, indeed, that could be a challenge. So in our work, we were focusing on sort of only focusing on those reachability-based safety. So what we did was when we were doing this, when we were developing the switching mechanism, we were only interested in the finite horizon, whether during the transition, whether the system will ever enter into unsafe state. Its long-term effect on the system stability is something that we did not study, but that is indeed a challenge. Yes.
All right. Wonderful. And thank you so much for that response. And thank you, Dr. Atkins and Dr. Koopman, and again, Dr. Zhu, for your contributions today and clearly the important body of work that we need to continue to research. This is all coming at us so quickly and rapidly, and there's so much opportunity. I know it's hard for industry, academia, everyone with an interest and value proposition to keep up with it. So we really very much appreciate the work that you all are doing. Okay, well, hey, gang, it is time for a break. And we will resume here at, let's see, what time are we resuming, everybody? 3:20. And that's when Huafeng will begin our next session on data assurance. Thank you.
Okay, we are a little behind the schedule, so we just get started. So this session is AI data assurance session, and we have 3 speakers. So first speaker, Dr. Feng Guo from Virginia Tech, and Dr. Yinhai Wang from University of Washington, and Dr. Panos Anastassopoulos from University of Buffalo. So let's move to the first speaker, Dr. Feng Guo. So we are all working in the data science side or statistics. So I will just make a very brief introduction of you, and let's get started.
Can you see my screen?
Yeah.
All right. Thanks, Huafeng, for organizing this session. I will talk about some of our research to using the real-life driving data to build test scenarios for automatic driving system testing and validation. So in terms of validate a AI system, one of the ideal situation, if we can test AI-based ADS in every possible scenarios, that's going to be ideal. But in reality, it's not possible. First, there's infinite number of scenarios. Exhaustively list all of them is not possible. Secondly, driving data has characteristics of big data rare event. We call that situation where majority of the driving scenarios are pretty benign, normal, low-risk situation, but there are relatively fewer rare corner cases. Those does not appear that often, but the majority of times, they are representing the major safety concerns. Like like Bill just mentioned in the previous presentation, if you like to find the statistical powers, you need an enormous amount of driving data in order to encounter enough safety critical situations to test your system. So the challenge we are facing is now with automatic driving and a lot of other OEM collected telematics data, the amount of data are there. So the question is, can we construct, I call it driving space, which is collections of all the scenarios. What does that space looks like? Can we use real data to construct this space efficiently? The second challenging or problem we're trying to address is how to systematically select scenarios for testing and training of ADS system. So again, those scenarios should have certain characteristics just to fit that infinite number of scenarios and big data rare event situation. So what are the challenges in doing so? Well, driving data is complex. If we just to describe the driving data, we know there are different sensors. There's videos, there's LiDARs, there's all the kinematic sensors. So they are high-dimensional, multi-model data, and they are highly correlated. For example, rarely you can see somebody driving like 70 miles in a 25-mile-per-hour neighborhood zone. And another example is like 0.6 G braking force. At low speed, it's probably okay. But if you're driving on highway 75 miles per hour, then you take a 0.6 G braking. It's a major event. So those variables are highly correlated. So you cannot simply change one single parameter to change the scenario. So you might get into a territory where in reality it's not possible. So another complication is that there are so many factors affecting driving safety. It's related to drivers, environmental, weather condition, traffic conditions. So just to describe this driving scenario is very challenging. So there are some research or frameworks to identify and develop driving scenarios. One of the famous one is the Pegasus classification of scenario by functional scenario, which are the natural language description of a particular scenario. For example, I'm doing lane change on a 45 undivided highway situation. All right. So the next little bit more details is logical scenarios. So in that logical scenarios, it require a concept called parameter space. So in this space, you instead of just one like natural language describer of the situations, you actually need the distribution of each parameters. Where when we construct concrete scenarios, we basically need precise, almost like frame to frame or second to second time series data to describe the entire scenario. So of course, on the left, you have fewer number of situations. Once you get to the right side, there's an infinite number of concrete scenarios. So the question is how do we select those scenarios? What does this scenario space looks like? So one of the ideas, one project we did is we're going to look at all this high dimensional driving data. So in this example, we are using all the kinematic data. And from this kinematic data, we extract the features, represent the key characteristics of this particular driving segment. All right. Again, because the data are highly correlated, multimodal, high-dimensional data, you cannot really directly see what the space looks like. Think about one scenario, include thousands of data points and images for that. And how can you explore this high-dimensional space? 1, 2, 3, humans still can understand. Beyond 4, it's almost impossible. So one approach we took is we use a encoder-decoder structure. So we put all these high-dimensional features, we put that into encoder and decoder and structure. And by minimizing the reconstruction error, we try to find a latent representation of the original data. So instead of thousands of original data points, now we can use a lower dimensional vector in three-dimensional space. You can think about that as one data point. And that represents the entire driving scenarios with thousands of data points. And from there, we can lower dimensional clustering, all kinds of analysis gonna be relatively straightforward. So from there, we can construct what we call scenario space. So the scenario space really is a collection of all the scenarios that's included in the data. And then when you select the particular scenario, instead of just randomly select, like this example I show here, include about 500,000 lane change scenarios. After reduce the dimension, we kind of see this point cloud that represent what the lane change scenario looks like. And going from there, then we can systematically select cases. So what are the driving scenario space looks like? Well, this basically three-dimensional, we can imagine they are a collection of data points. And by clustering them into different subspaces, each represent a particular driving scenario. For example, this red line means represent a driving scenario of moderate speed, but relatively jerky driving situations, where this brown plot, and from the radar plot, we can also see they represent relatively high speed, but smooth driving scenarios. So each of those subspace has certain characteristics. Now with this, instead of dealing with hundreds of thousands of individual driving scenarios, we have a way to visualize and to see the relationship between all the data points at different scenarios. So this provides a base for us to do systematic sampling for test and validation. And furthermore, we can, for each of the subspace, because once we reduce the dimensionality of the data, now we can actually estimate the density within that subspace. So here in this example, the darker blue part is the high frequency. They happen at much higher frequency, where the light blue means low density areas, corner cases, relatively rare, does not happen that often. And the red dot are the safety critical event we can identify. As you can see, most of times they are at the edge or corner of this distribution. So with this, we kind of have a relatively easy say, hey, the driving scenario, driving space looks like. Next question, how can we systematically select data points from this for testing or training purpose? Well, the motivation is, well, random sample probably is not a good idea because in the testing scenario, think about a test track study. Eventually, you like to test your system in a real driving environment instead of just in a virtual environment. Those test track studies or field studies, they are very expensive, resource demanding. Typically, you can only afford a limited number of tests. So how the quality of those test cases will be critical. For training purpose, because the majority of the cases, there's a severe data imbalancing issue because rare event, high risk scenarios happen at much lower frequency compared to high frequency data points. So if you're training the data, it's going to be overwhelmed by these normal driving situations. So once they see a rare event, they might not deal with that well. So for each applications, we like to have relatively balanced representative sample. And the question becomes, how should we select those cases? Well, the idea we have is there are two criteria we can to select. One is what we call criticality. So in this criteria, basically, we like to have good coverage for the entire space. If we just do total random sample, most likely you will only get data point from the high density middle part of the data. So criticality basically can ensure we cover the entire space, and each selected cases represent a distinct area or subspace of the driving scenario space. So that gave us the criticality, good coverage for the entire space. The second criteria we are interested in is we call that representativeness. Again, in terms of evaluate system performance, the weight for each of these case should not be the same. If this is a very common case happen much more often. If the system failed for these common cases, there should be a big penalty. Because every day you're gonna meet this situation at least once. If you cannot pass that, almost immediately get out, you get into a crash. Where these corner cases, relatively rare cases, their penalty, if you mess up one of them, it might not be the end of the world because they happened at much less frequency in real life. It might take like years to experience one. So the penalty for those each of the select point should be different. So this is the representativeness of the sample. So in another way, put it another way, this sample should represent the distribution of this driving scenario space. How do we do that? One approach we take is using a kind of two-step process. The first step, as I just discussed, we can prepare the candidate test pools. So this is a collection of all the driving scenarios constructed from the real-life driving data. For example, the example I just showed was using the SHARP2 NDS from more than 1 million hour of continuous driving data. From there, we can easily get 500,000 lane change scenarios. So we construct that space. And from there, first step is we select sample cases following the criticality criteria. So the idea, we use a particular matrix is called information potential. So information potential basically can measure the similarities between each of the data points. So by optimize the information potential, we can select points that are sufficiently different from each other. And that will basically provide a good coverage for the space we're trying to sample. The second step is to assign weights to represent the driving space distribution. So for this purpose, for each of the select cases from the step 1, we use a particular measure called maximum mean distance, MMD. It's a measure of the distance between two distributions. So we assign each of the selected case a weight, and then measure that the distance MMD of the samples with the original distribution. We try to minimize that distribution. Through this minimization, each data point get a weight, and that weight represents how common this particular case is. By doing this, we provide a framework, be able to get a subsample of cases. First, provide good coverage for the entire space. Secondly, from the weight of the samples, we can retrieve what the original distribution looks like. And when you're doing test or training, use these selected samples, it will provide a much more concrete coverage for the entire driving space. So here are examples we used. So from here, use the SHARP2 naturalist driving study. So here we sample 821 crash events and more than 12,000 normal driving segments. And by construct the space, we can see from the left side, this is from two-dimensional space. This is what the candidate testing pool or subspace looks like. And through our sampling scheme, we can see that the red cross are the selected samples. The size of that symbol represents the density, the weight associated with that. So it provides a pretty decent coverage especially for the corner case and tail part of the distribution, where if you just use a regular density estimation, because the data is so sparse, you cannot even see that from the density plot. But through this two-step process, we can actually identify all these data points. So this is based on video data and the vehicle kinematic data. This can be done relatively easily, but beyond this regular telematics data, there's also another data sources currently we are looking at. One is the crash database. So crash database, each of the crash narrative contains valuable informations. Again, this is to address the issue of big data, real event situation, where crash data happened every year. This NHTSA maintains a crash database. There's state level police report, and all these narratives in the data actually contains useful information. So we follow the similar concept, but instead of using a decoder framework, we put that through the large language model. So to get a latent representation of the crash narrative. So again, in this crash space, what I call each data point in this space represent unique crash situations. Again, you can sort of see they form different clusters, different groups. And if you look at one of them, like this one is further away from all the rest of the data. Those are not surprisingly related to deer and animal crashes. So those type of crash are quite different from the other crash types. So combination of this crash space and the driving space will hopefully give us a comprehensive understanding of what the driving space looks like and where the risks are. Some of the most recent works we are looking at is user vision language model. For example, we are surprised to see some of the information we get from that has a human-like scene understanding. Here's one example. Instead of just calculating numerically time to collision, all these risk factors, when you ask what are the collision risks in this frame, the response is risk is low. However, this is by assuming that the vehicle parked over there, okay, will remain parked. And there's no unforeseen actions, such as suddenly open a door or pulling out into the traffic. So those kind of understanding for scene behavior, those require general knowledge. Those are what human drivers see, will understand the risk. But if you just use the videos or the kinematic data, it's very difficult to derive this, to sense this kind of risk. I think the framework I just discussed can easily incorporate this part of the information into the framework. So here's a quick summary. So I think the data-driven test and validation ADS, especially use real-life driving data, is valuable in guided scene selection, and advanced analytic method really can benefit the space construction and case selection. All right. Dr. Yu, back to you. You are muted. Dr. Yu, you are muted.
I'm sorry, yeah, I'm muted. Yeah, thank you so much for the great presentation, and you shared a really great insight on the data analysis and the different considerations. We do have several questions on the chat window, so I just take one very quickly. So one, we do have very good comments from Phil. Probably can read the chat, and one question from Ganesh Pei. For the current slides, I don't remember which one. If lower frequency but ultra high criticality events are weighed less for sampling, that is representative probably of operating environments that may be encountered but is not representative of what the function must provide. Shouldn't the sampling be based on the intersection of the two? You are muted.
Yeah, sorry. Definitely. The sampling be based on intersection of these two. The sampling will cover both criticality and representativeness. The representativeness, the criticality of that definitely will be considered when we do the evaluation. For example, if you test the ADS system with high criticality, depends on how important it is, how rare it is. We can give it a different score based on how well it's done in that situation. Again, the intersection of these two is definitely we should consider both factors.
Okay, thanks again, Dr. Feng Guo. I really appreciate your presentation. So now let's move to the next poll question.
All right, so thank you, Huafeng. So moving on to question 7. There are 2 parts to this. So question 7A is, to what extent are mechanisms in place to ensure the quality and integrity of the data used in AI systems? And we'll take about a minute for the question.
Yeah, so I think, is this question for me, right?
No, this
for
is
the whole
poll.
audience.
Yeah.
Okay.
Of course, you can answer with your phone.
Yeah, I think what I presented is just one way of looking at that. Way to visualize and construct the space. I will leave that to the rest of the panel.
Yeah. These questions are very critical for us to understand the current status from both academia and the industry perspective, and particularly the audience experience. And that will be very, very important for us to make our plans for the future AI assurance research or project.
Okay, so I know that we only have 51 people who have responded, but let's quickly take a look at the responses, and I will keep this question open after we look at this. So I think majority of you said that mechanisms are in place to a small extent, so which I think more work is needed here, according to the respondents. And so moving on to the second part, which is 7B. And so here, the question is, how effective are the existing mechanisms in ensuring the quality and integrity of the data use? So the previous one was whether the mechanisms are in place. This one is how effective are those mechanisms? And so you again have about a minute to respond. Looks like people had already moved on to this one and responded, but that's good. Ten more seconds. All right. Let's look at the responses. Oh, not too effective. Yeah, I guess that's why we have this workshop, right? So yeah. So I'm just going to keep these, the responses. I'm going to keep it on, just so people have an opportunity to respond to it. But I will stop sharing Huafeng.
Yeah, thank you. And this is really a good motivation for us to work on data assurance. So our next speaker is Dr. Yinhai Wang from University of Washington. Yinhai, could you share your slides?
Sure. You see
Yeah,
my window
perfect.
now?
Yeah, perfect.
All right. So good afternoon, everyone. So thanks, Huafeng, for putting this together and the opportunity to share my view and our research at the University of Washington. This is certainly a very important issue, and AI is a hot topic. A lot of people are really interested in trying AI, applying AI. So the left side picture actually is showing a picture of the workshop organized by the AI committee of TRB at the 2024 TRB annual meeting. So this room can hold about 100 people, but there were over 200 people, in this room, and try to join this workshop, and it was really crowded. And the right side picture is actually showing a recent event that we organized. The TRB AI committee and two university transportation centers collaborated with the Texas DOT. We put together an AI in Motion Symposium, Shaping the Future of Mobility and Safety. So we started to plan for this about February, and this event was in May. We were able to attract over 150 people, and 13 companies committed to sponsor. So we got a lot of interest. So even though the time was short, but we gather people from agency, company, and also universities. There were a lot of very interesting discussions about how we could move AI forward. But very clearly, there are a lot of challenges that people may not be aware. So in transportation field, we have many very hot applications, but basically these 6 methodologies listed on this slide are the most popular ones, such as generative GPT, recommendation system. For example, those methodologies used for Uber and Lyft are typical examples of a recommendation system. Reinforcement learning. So this is a common methodology we train like algorithms how to perform in a particular way, such as we use human driving behavior data to train autonomous vehicles how to perform like a human. Long short-term memory approach, that's also very popular and common, used for like a traffic flow forecast and a lot of other prediction-related research. Explainable AI is very, very hard. So the AI committee receives over 250 papers in the past 2 years. And we try to put together podium session. And so this explainable AI is always on top. People want to know more about this, and they try to avoid using a black box approach. Computer vision and edge AI is another very, very hot area. So you see a lot of very successful applications in our field. So these are wonderful examples, but certainly we have a common question about the importance of data and whether the data we collected and applied are good enough to support a successful AI deployment. Data is very critical. So, we use data to train the AI model. We also use the data to continuously improve the model, validate the model. So if we provide biased data in the training process, so the model is likely to be affected and perform biasly. So I'm actually in Oslo for a workshop, and this morning we actually went to Autonomous Vehicle Research Institute, and we learned about an ongoing project in Oslo. And the person who showcased their autonomous vehicle research told us, their original algorithm was trained using the data collected from Mid-East area taxi drivers. So when they deploy the particular methodology in their autonomous cars, so the car performs like Mid-East taxi drivers. So they have to make a lot of adjustment, try to make it perform more like a local driver in Oslo. So I think this is just example showing the importance of data. And if we want to make sure the AI deployment is successful, there are a lot of work needed to make the AI model perform in a very reasonable way. So looking back to the transportation research history, we started with almost no data, right? So most people know this person is Bruce Greenshield. He's the first person actually started to collect traffic data and also research traffic flow. So he published his first paper in 1933. And this right side picture is showing Bruce is actually collecting data using a camera and also a clock, try to see where the vehicle is and then gather the vehicle position and timing and try to calculate speed. So over the past years, so certainly we see the value of the data and we deployed a lot of traffic sensors. So these sensors listed on the top of the slides is actually the common methodology that the DOT uses. For example, the loop detectors, video sensor, radar sensor, infrared sensor. But these are location-based detectors, right? So you can imagine the data you collected from a particular location. It does not see the vehicle's movements from one point to another. It only see basically a snapshot at a particular location. And in the recent years, so we get more like data sources. For example, the Internet of Things, we can use the sensors information and try to produce traffic information, traffic data, like people's cell phone, people's Twitter message, posts on the social media, like Uber, Lyft, or other kind of shared resource vehicle, autonomous vehicle, even the garbage can, it may have the MAC address reader, right? So it also gather traffic data. So we get a lot more data, but most of our transportation models are based on a lot of mathematical assumptions that was developed at the moment. We do not have a lot of data. Now we have more data available, and people would believe these are the data we should use with trust and try to build big data models or like the AI approach produced from the observed data. But I think this session is a very good session because we really want to make people aware. Even you gather data, the data is not perfect. The data may still have various kinds of problems that we call bias. Here I want to give you two examples to show the impact of data bias. So the left picture shows the autonomous vehicle crash happened in 2018. So basically, the sensing algorithm deployed in this Uber autonomous car failed to recognize a crossing cyclist, and then the crash happened. So we can talk later. Bicycle users are not very common in the active user data collected, and therefore the methodology may not be good at recognizing this kind of user. Another example is actually also widely reported in media is Amazon's AI recruitment tool algorithm. So basically this algorithm was trained by like 10 years of data, the resume of job applicants. And then the AI approach try to process people's like an applicant's resume and try to pick up the top ones, because the knowledge was from the previous, submitted or like hired workers. So they believe this is actually the methodology they're supposed to be choosing the new job applicants for a further review. But because female was underrepresented in the past data, right? So the AI approach actually carried that knowledge. And in the application, people found this particular methodology actually discriminated women. And therefore, Amazon stopped using that. But this is another example, you use biased data and the new methodology is going to carry the bias into the next practice and maybe generating unbiased, like generating unfair results. So no matter what we do, we just cannot completely eliminate data bias. So when we apply AI model, we have to consider what kind of potential bias this data set may carry, and how do we mitigate the impact of the data biases. I see a survey question about these things, and I do believe this is just at the very beginning, and I'm not aware of a commonly accepted approach to deal with this issue, because each particular problem could be very different. So I would encourage researchers and application agency or companies try to look at your own specific case and see what is the best way to address your data bias. But here, I do want to share through our past research what we have learned. We found a major source of data bias is actually from the unbalanced sensor deployment. For example, if you look at the data you collected in the urban area, you may have a lot of sensors deployed, and you have more data. You understand what's going on. But in the large rural area or underserved communities, you may have no sensor at all. So in this case, if you understand the overall situation better, you have to consider there's a large area without sensor data or without the traffic information input. So in developing a model, you have to consider that factor, right? Or maybe you could consider more balanced deployment of the traffic detectors. Another important source of data bias could be from weather and other environmental factors. For example, the left side photo is showing there are 3 vehicles, but using the YOLO approach, you just use this particular image, you only detect 2. But if you process one more step, you try to dehaze, get rid of the kind of airborne small particles impact in viewing the particular objects, and then apply the same approach. You can see actually the middle image, you started to see 3 vehicles. And the right side photo is actually showing our research. We just grabbed the YOLO approach. This is actually a very popular methodology developed by computer scientists. And you see, you implement the model, you detect the number of pedestrians crossing the road. You can see actually quite a lot of pedestrians are missed, right? So you see only very few, maybe about half of them are marked with the label. They are detected. So we'll show you the same scenario, but with improved approach. You can see actually more pedestrians are detected. But that shows another important thing, when we try to address the data bias and try to mitigate the impact, we could do something with our AI approach as well. So the third common challenge is actually from this so-called a natural long tail distribution. So this is a common issue. For example, when we apply this to active user detection, we know for the pedestrians detected by the sensors, most of them are actually walking pedestrians, right? So very few of them are actually sitting on the wheelchair, but the wheelchair users are also part of the active users. But if you don't get a lot of these users, when you train the model may not consider wheelchair users is part of this and need to be treated seriously. They may actually just consider we satisfy the walking pedestrians detection accuracy, we can get the best loss function, and therefore that's the best model. So I think that is an issue very common in training our machine learning methodologies. And the one shown on the slide is actually the 13 class of vehicles that Federal Highway uses, right? So you see most of the vehicles are in category 2 and 3. So if you gather, like, for example, you process 10 hours of video and gather the vehicles out and try to label the data, you will find actually most of the vehicles you labeled are in class 2 or class 3. You have very few in class 1 and even fewer in like a class 12. So and class 13. So how do we address this challenge? If you don't address this challenge, so the model developed will be doing a very good job, maybe for class 2 and 3, but they may not recognize like class 1, class 12, class 13, this kind of categories with very few examples. So how do we actually apply a particular approach, try to mitigate this kind of impact of data bias or reduce the data bias? Through our research, so we consider these steps may be important, right? So looking at the transportation system, you have infrastructure, you have user, you also have vehicles. So you want to make sure, you gather the input from all these groups, right? So you deploy the sensor in a reasonable way. And then the input, like the scene captured by your sensor, will be processed, right? So you have actually one level of machine learning methods try to recognize these users. And the data could be further processed, like on cloud or on the edge computing equipment. And then you use the data to train like your AI model, right? So there are certainly the major data bias sources mentioned earlier will all present here. But what we recommend will be these several important things to consider in your approach. The first thing is, when you decide to instrument a particular infrastructure and try to gather data, you need to consider how do you balance, the sensor deployment. And after you get that, you want to also make sure there's a cyber physical cooperation. And so you can gather the data, you can trust the data set, reduce the impact from the environmental factors, as mentioned earlier, right? Like the foggy days, the rain or other factors. And the last step is to make sure your model will be able to address this long tail distribution challenge we see very common in our transportation applications. So here I want to use some examples to show how we deal with these things. The first example is actually how do we instrument the sensing technology in the underserved area. So this is actually from one of the research projects we collaborated with Yakima Nation and the Washington State DOT. So Highway 97 goes through Yakima Nation is a very dangerous corridor. So in 16 miles of road from Union Gap to Toppenish, there are normally over 20 serious crashes a year. So we put some sensor there, we gather a lot of very valuable data. But before this, there was no traffic sensor. We see all the crashes, but we do not know exactly what's going on. You see actually the picture at the lower right side. We found this particular intersection is so small, but over 70% of the vehicles are large trucks or agricultural vehicles. So when they make the turn, it's quite a dangerous movement. And this also have a lot of weather challenges like snow, ice. So we understand this better. And then when we try to analyze the crashes, we have some fundamental data to use. I think this will be a lot helpful, to make a wise decision to address the safety challenges. And this particular effort, actually, we received the Federal Highway Build a Better Mousetrap Programs Innovative Project Award. So another thing I want to emphasize, talking about, how do you address the sensing process to get rid of the potential impact of the environmental factors? Like in this particular example, right? So you see the left side picture is not clear. This is because there are a lot of fog or like a small airborne particles, blocking the side ray to reach to the object. But if we apply our dehazed methodology, you see the right side is a picture after we remove that, right? So by doing this, we're able to generate like the roadway visibility and also detect better on what's going on the roadway, number of vehicles there, and also how do we understand like the roadway surface condition. So this slide shows actually we apply the original picture on the upper left side, and then the middle is actually after we dehaze the particular image, and the right side is scattered map. Is actually we remove this scattered map from the original image, and you can see the original roadway much better. And by comparing the density of scattering map, you'll be able to understand the visibility. And you see like the right side, there are two pictures, right? So original and after you do the dehaze. By doing so, you can reduce the data bias. Otherwise, in this kind of weather condition, you may not gather the data you want. Yeah, so I showed you this intersection detection, right? So using just the regular YOLO approach, you miss a lot of pedestrian. But after we develop our own approach, it's called a scale-aware representation learning empowered sensing system. We actually captured almost every pedestrian. So the left side is showing a flow chart. I don't want to explain further about that. Basically, the idea is you detect where there are pedestrians, and then you use another model, try to go deep to see how many pedestrians in that particular segmented area. And so you see this particular customized approach for transportation application produce much better results. So in general, how do we address these data challenges, right? So from the modeling side, we can still do multiple different things. The first thing we could do is we call it class rebalancing. You may have a lot of data in one category, maybe very few in another, right? So you could do undersampling, try to make the number of representations similar from like both categories. And you could also scale up, right? We call it oversampling, try to make more samples there. And you could apply a decision tree, try to make sure, this overall approach is fitting the particular application well. So let's visit back this 13 bin vehicle example, right? So we have a lot more vehicles in class 2 and 3, very few in like class 11, 12, 13, and 1. So our approach is basically you layer the different detections, right? You try to detect what kind of vehicle. So if we say this is a single unit trucks, right? So you have 5, 6, and 3, and you will be applying the data directly to this small group. Just try to separate this single unit truck is in class 5, 6, or 7, right? So by doing so, by doing the layered detection, you can address this like a long tail distribution problem much better. So maybe using a day life example, it's just like you go to your like a family doctor. It may say, hey, you have maybe this problem. You need to go to see a specialist. And the specialist will be another layer of model, just using the data collected for those categories. So you apply that and try to process again. I think this will be addressing a lot of these challenges. And this is actually—
Dr. Wang, yeah. We may run out of time. How many slides do you have?
I'm wrapping up very quick. Yeah.
Okay. Thank you.
This is actually the detection accuracy. You can see actually by applying that layered approach, we get much better result. And so another approach would be like information augmentation, right? You could use limited data by applying transfer learning, data augmentation, feature augmentation. You could increase the sample size. So this is actually example for doing that. And a good example we tried is actually we developed an approach called de-biased traffic object recognition. And this particular methodology tried to recognize those unusual like objects like wheelchair users, like animals crossing the road. And you see actually the rightmost column showing, the results is much better than existing approach. So even this is not ideal, like it's only about 50 to 70% accuracy, but much better than before. So that's pretty much my quick overview of the research work we did and my idea about how to address these challenges. Thank you.
Yeah, thank you. Yeah, thank you so much, Yinghai, for the presentation. I know it's very late for you to call from Oslo, so I really appreciate you attending this workshop and give this presentation. It's really what we want to learn from you. We run out of time. If you have some time, could you answer the question directly in the chat window? There are several comments and questions.
Sure.
Yeah, so we just move next to the poll question.
Okay.
Thank you, Yinghai.
Thank you.
Okay, so I can move to the poll.
Yeah.
All right, so this is question 8. And so end users have sufficient information about data powering the AI systems to make informed decisions about whether and how to use the system's outputs. So do you agree with this statement? And I'm going to set the timer for 1 minute. Twelve more seconds. All right. Let's look at the responses. Oh, strongly disagree.
That's why we have a big needs.
Yes.
Data research.
Yep. I'm going to keep the responses on, just in case folks didn't get an opportunity to enter their poll.
Okay, that's great. So yeah, next we will have our last speaker. I know it's a long day, and thank you so much for staying on, still in the session. Our speaker, Dr. Panos Anastasopoulos from University of Buffalo. Thank you, Panos. Yeah, to give this presentation.
Can you
I can hear you
screen?
and see you.
Okay, perfect.
Yeah, I can see your screen. Yeah, perfect.
All right. Well, welcome everyone, and thank you for joining us today. I'm Panos Anastasopoulos, and I'm with the University at Buffalo. Today, I'm excited to give this brief, with an emphasis on brief, presentation on integrating statistical modeling with deep learning in transportation safety research. Let's start with an overview of this brief talk. We'll begin by discussing the roles of artificial intelligence and statistical modeling in transportation safety. Then we'll explore the concepts of prediction versus causality and how AI and statistical modeling can be fused. And finally, we'll talk about the future implications of integrating these technologies. Statistical modeling employs statistical techniques to analyze data, understand relationships, and inform decision-making. Econometric modeling is a specific form of statistical modeling used to analyze economic data and predict economic phenomena. These models are crucial for understanding various aspects of transportation safety, and they can guide our efforts in improving it. Some key applications of statistical modeling in safety involve forecasting the likelihood of accidents based on historical data, assessing how well safety measures are performing, identifying and prioritizing risks and appropriate responses, evaluating the impact of various safety interventions, and comparing safety performance across different regions or time periods. On the other side, artificial intelligence simulates human intelligence in machines, enabling them to think and act like humans. A subset of artificial intelligence is machine learning, which involves algorithms that learn from data to make predictions or decisions. Deep learning is a further subset of machine learning that uses artificial neural networks with multiple layers to learn data representations. Artificial intelligence also has numerous applications in transportation safety, including enhancing vehicle safety through advanced AI systems for connected and autonomous vehicles, preventing accidents by detecting potential collisions, identifying vulnerable road users like pedestrians and cyclists to avoid accidents, tracking and analyzing driver behavior to improve safety, and monitoring and assessing road conditions to provide timely alerts and maintenance. Integrating AI and statistical modeling in transportation safety research presents several challenges. Let's go over some of these key areas. First, data quality and quantity. AI models need vast amounts and high quality of diverse data to make accurate predictions. This is because poor data quality or insufficient data can lead to unreliable models. Similarly, statistical models depend on good quality data to uncover meaningful relationships and estimate the parameters accurately. Next, in terms of interpretability and transparency, AI and especially deep learning often act as a black box. I'm sure you've heard that many times today, which makes it hard to understand the decision-making process. On the other hand, while statistical models are more interpretable, complex data relationships can still pose challenges. To that end, statistical models should be carefully specified and validated to accurately represent the underlying phenomena. In terms of robustness and reliability, AI models must be robust and reliable, which requires extensive testing and validation, especially in critical applications like transportation safety. Similarly, statistical models need rigorous validation and calibration to ensure accurate predictions across diverse scenarios. In terms of ethical and legal considerations, AI systems must navigate ethical and legal issues such as data privacy, algorithmic bias, and accountability. Statistical models face similar challenges in avoiding misspecification issues and statistical bias, but also in ensuring ethical outcomes. In terms of integration, integrating AI into existing systems involves technical integration and making AI user-friendly for practitioners. This is very important. Statistical models should also be accessible and interpretable by non-specialists, and this often requires the development of user-friendly tools and interfaces. Lastly, in terms of the role of the human element, AI should complement human decision-making by providing transparent and actionable insights. Similarly, statistical models should support human decision-making with clear and interpretable results. So by addressing these challenges, we can get closer to a possible integration of artificial intelligence and statistical modeling in our effort to enhance transportation safety outcomes. Now, when we attempt to integrate artificial intelligence and statistical modeling in transportation safety research, it is important to understand the distinction between prediction and causality. For example, artificial intelligence prioritizes prediction over interpretability. It excels in forecasting accuracy and in handling complex data patterns. Particularly, deep learning algorithms do very well at capturing and modeling complex nonlinear relationships within the data. This capability allows artificial intelligence to make predictions that might be missed by simpler models. Now, while artificial intelligence is powerful in making predictions, it often functions as a black box, as I mentioned before, which means that it can be challenging to interpret how the model arrives at its predictions. This can be a drawback when we try to understand the underlying causes of safety issues. On the other hand, statistical modeling is more effective at identifying and understanding the causal relationships among variables. For example, statistical modeling can help determine whether poor road conditions directly cause an increase in accidents, which is crucial for designing effective interventions. At the same time, statistical modeling requires explicit assumptions about the data and the relationships between the variables. These assumptions make the models more interpretable and allow for hypothesis testing, which is essential for establishing causality. By combining the predictive power of artificial intelligence with the interpretive strengths of statistical modeling, we can create models that not only predict outcomes accurately, but also provide insights into the causal mechanisms that drive these outcomes. For example, artificial intelligence can identify high-risk scenarios for traffic accidents, while statistical modeling can explain why these scenarios are high risk, which can in turn lead to targeted and effective safety measures. Such fusion should be achieved through several key steps, and the very first step is data pre-processing and feature engineering. Before any model training can take place, we need to pre-process the data. This involves cleaning the data, handling missing values, and transforming the data into a format that is suitable for our analysis. Feature engineering is a critical step where we create new features or new variables that can help the models better understand the underlying patterns in the data. For instance, in transportation safety, we might create features that capture weather conditions, traffic flow, or driver behavior. Once the data are prepared, we can use deep learning models to train on this data. These models can then be used to make predictions. For example, predicting the likelihood of accidents under various conditions, which can help in proactive safety measures. Next, it is important to quantify and understand the uncertainty associated with these predictions and to evaluate our models. This involves the use of statistical techniques to quantify the confidence in our model outputs and the use of various metrics like accuracy and precision to assess the performance of our models. This helps us to better understand how well our models are performing and where improvements are needed. Finally, we need to draw meaningful inferences from the models, as this is crucial to making data-driven decisions. And of course, this involves interpreting the model results to better understand the factors that contribute to safety outcomes. By combining the predictive power of artificial intelligence and the interpretive strength of statistical modeling, we can derive actionable insights to enhance transportation safety. In the next few slides, I would like to provide a framework on how we can possibly achieve this fusion of artificial intelligence with statistical modeling. The first application of this fusion is the evaluation of the prediction outcomes from the deep learning models using statistical modeling. Let's say that we would like to assess accident occurrence and injury severity to improve safety. We can start by using deep learning models that are trained on large data sets and predict the likelihood of accident occurrence or injury severity outcome. However, our predictions need to be evaluated to ensure that they are accurate and reliable. To do so, we can use statistical modeling, and we can assess these predictions against real-world data by identifying any discrepancies and by understanding the factors that the deep learning model might have missed. This evaluation process is iterative, which means that we continuously refine the deep learning models based on the insights gained from our statistical analysis. This ensures that our models are not only accurate, but also robust and reliable over time. The second step in our framework is to use the factors identified through statistical modeling to inform and enhance the training of our deep learning model. This can improve the accuracy and reliability of the AI system in predicting safety outcomes. In simple words, this step explores how factors affecting safety can inform the training of our deep learning model. Our statistical model can help identify key factors that significantly impact safety, such as road conditions, driver behavior, and environmental conditions. These factors can then be used to inform the training of our deep learning model. By incorporating these factors into the model training process, we can ensure that the models are more attuned to the nuances of safety dynamics. For example, if our statistical analysis shows that certain road conditions significantly increase accident risk, we can emphasize these conditions in the training data. This will help the deep learning model to better understand and predict the safety outcomes under similar conditions in the future. This process of using statistically identifying factors to inform deep learning model training is anticipated to lead to improved prediction accuracy. The models will become better at identifying high-risk scenarios and in predicting potential safety issues before they occur. The third and last step in our proposed framework is the recurrent enhancement of our deep learning model based on the statistical insights. This continual improvement loop can significantly boost the performance of AI in predicting and mitigating transportation risks. So, briefly, in this step, we use the insights gained from our statistical evaluation to refine the deep learning model iteratively. This means that we continuously update our models with new data and insights to improve their predictive performance. For example, if new data indicate a shift in accident patterns due to seasonal changes, this information will be fed back into the model training process to keep the models up to date and relevant. Now, establishing a feedback loop where the results of our statistical models inform the deep learning training process and vice versa is very important. It's crucial. This ongoing process will help us identify any biases or errors in the models, allowing us for corrections and adjustments even in real time. And through this feedback loop, we will achieve enhanced performance of our deep learning model. The model will become more robust, more accurate, and more reliable in predicting safety outcomes, which in turn will ultimately lead to better safety interventions and policies. This iterative enhancement will also help us develop more sophisticated models that will be capable of addressing increasingly complex safety challenges in transportation. As we look into the future, the integration of artificial intelligence and statistical modeling seems to have great potential to help us solve existing and future transportation safety challenges, from long-lasting issues to problems that we have not even thought about, we have not even imagined yet. Predictive analytics can help us participate and prevent accidents before they occur by identifying potential safety hazards. Real-time risk assessment tools can support decision makers with timely insights, enhancing safety measures on the go. Because it is crucial that AI-driven decisions are transparent and understandable, explainable AI, as previously mentioned, will help us ensure that we have more trustworthy and clear insights into how decisions are made. At the same time, we should leverage data-driven approaches, which will allow us to evaluate and refine policies effectively. This iterative process will lead to a more effective and tailored policies. In summary, integrating AI and statistical modeling offers a huge potential to revolutionize transportation safety research. By embracing these advancements, we can create safer and more efficient transportation systems for the future. This concludes my presentation. I hope this has provided some insights into the potential of integrating statistical modeling with deep learning in transportation safety research. Thank you for your attention, and I look forward to a fruitful discussion.
Thank you so much, panels. This is a very interesting talk. It's really an area that we want to explore in depth in the future. And we do have some questions on in the chat. We have, I know it's very late for the Eastern guys. We probably just skip the question session. If you want, please answer the question in the chat.
Sure, we'll do that.
And I really want to thank you all the three speakers, Feng Yinhan and the panels. These are really great talks for us to learn what you have for research, and we also think about how to collaborate in the future to develop the data assurance methodologies to mitigate AI risks for transportation. So thank you so much, and this closes our session of AI data assurance, and I will just turn over to Taylor to wrap up for today's workshop.
All right, wonderful. So right ahead, we're going to go ahead and ask the final poll question of the today. So we're going to go ahead and put that up. And while we get that poll question ready, what a wonderful day. This has been fantastic. I think I've learned a lot. I hope you all that committed your day today with us learned a lot. But let's go ahead and Meenakshi, why don't you read off this question? So how much?
Yeah, sorry about that.
So, lost it.
I lost my, yeah, 1 second. Okay, all right. So how much has your level of understanding of AI assurance, foundational concepts and challenges improved over today's workshop?
Great. So while we have this question up here, tomorrow we're going to kick off again at 11:30 Eastern with some welcome and introductions, and we have a keynote speech with Brian Cronin from the ITS Joint Program Office, Director. And then we're going to move into a panel discussion on AI assurance and research needs and priority, followed by 2 more technical sessions focusing on the final 2 components that we identified in the workshop to target, which is design time assurance as well as operational time assurance. And then we'll wrap up tomorrow with the reflections and wrap up on what did we learn, what did we see, what did we hear over these past 2 days that can really help us, move forward as we all work together as a community in this space of AI assurance. So as we conclude for the day, we can go ahead here and we'll go ahead and post these results. And let's see with our 42 votes here where we stand. Great, all the way shift left. This is a great sign here. I'm hoping that the value of these workshops are going to be very helpful for you all. Again, we're all learning. We're a community together of researchers, engineers, and scientists, making a difference for AI assurance. So thank you all for coming, and we really look forward to tomorrow's day 2, where we're going to have a really amazing day. So everybody have a wonderful afternoon. Thank you very much for attending.